All right, so hello everyone. Thanks for coming to today's lecture. Just test 1, 2, 3. Is everything good? Can you see my share screen and also hear my voice?
Yes.
Cool. All good. Thank you very much. All right, so before we start today's lecture, let's talk about two things about the group project. One thing is for the group who would like to work on the real robots. Then I've already submit my request to the Mechatronics Studio. Then the Mechatronics Studio will arrange everything for you. All right, but please give them a little bit of time to arrange it because in the current situation, what they can do is they can lock the robots in the locker in Mechatronics Studio, and every time you have to go to the Mechatronics Studio to work on that. All right, so I've talked to the guy who take charge of the Mechatronics Studio. In the current situation, we can't let you to bring the robots back to home. That's the problem. So every time you want to work on the real robot, you have to go to the Mechatronics Studio. And also because of the social distancing, so there is the maximum number of students who can work in it. So they have to make a timetable for you, something like this. And then when I get things replied from them, then I will send you as soon as I got it back from them. All right. So that is one thing about the the projects working on the real robots. And during this time, if you're working on the real robots during this time, it is better if you can do some preparation on the other parts of the project instead of working on robots, because you don't have it at the moment. Then you can do some kind of like algorithm development, or you can work on the simulator first, and then until you can get access to the real robots. And for the students who are working on the DoBot, you definitely need to work on the real robots because there's no DoBot simulator. So please wait a little bit, and you can develop things on the algorithm part first, and then when the robot is ready, you can test on that. All right, and for the students who are working on a fetch robot and would like to work on the real robots, you do have to work on the simulator first, because the fetch robot is bigger and it's more dangerous. So you have to work on the simulator only for the fetch robots. So if you would like to work on the real robots, you do have to work on the simulator first and demo to me. Everything works well. Then I will ask one of my a tutor or my PhD student, to help you to move your thing onto the robot. But the thing is, before you move thing onto the robot, in the fetch simulator, you have to demo everything works. All right, so that is one thing for the group project. And another thing for the group project is the meet review report is due in 2 weeks. So the deadline of the meet review report is by 20th of September, which is in 2 weeks. My previous experience in the last semester is, if you want to have a relatively good mark for the group project, then you need to consider this meeting report as well. Because I do have some of the groups, they've done a really beautiful project at last, but I think they start doing the project after the deadline of the meeting review report. So which means even at last, they've done a really, really beautiful group project, but at the time that when they start making the meeting review report, they can't write anything because they didn't done anything. They haven't done anything. And which means that 5% they can't get it, or they can get a very, very low mark on that 5%. Then totally it will affect the total mark of the group project. So what I mean is, so there are different deliverables with different marks on it, with different percentage on it. And the next one is the mid-review report. And I do suggest you to work on something. Don't put everything into the very last 1 or 2 weeks. So start doing something, then you have something to write into your mid-review report. Then you will get marks from it. But if you haven't started doing anything, and even you did a very good job in the last 2 weeks, you finish a very beautiful project, but you can't write, because you haven't done anything, you can't write things into the mid-review report. Then you can't get marks on it. This is what I suggested. All right, and the mid-review report is submitted per student instead of per group. So which means each individual member will write your own mid-review report with the works you've done by yourself, not the others. All right, so try to work on something and to write a good mid-review report. That is my suggestion. All right, so before starting, any questions on that? A format, that's a good question. So a mid-review report, there's no limit about the pages, but what I mean is for the mid-review report, you need to write what you've done, the work you've done. All right, so including everything, the algorithm, the literature review, the algorithm you use, and the experiments you've done, something like that. It shouldn't be a very complete experiment, but you may test something. You may test some of your work by partially getting some data, something like that. All right. So, for example, if you're doing a fetch robot following the person in front of the robot, then suppose you are doing the collision avoidance part, for example. Then you may need to test something offline, right? Suppose in the simulator I get some obstacles, then when the robot's driving in, it has the ability to avoid the collision of the objects in it, something like this. Or for example, if you're working on the turtle board following a straight line by observing some markers or something, right? So one of the member may work on the marker detection and some kind of like post evaluation or something. Then you can definitely work on that offline with some pre-logged videos or some pre-logged videos or images, right? And another person may work on the video serving part. Then he can also work on this video serving by logging some offline data, or even only test the algorithm with some designed images, right? Something like this. So you have to write what you've done, not the others, only by you, what you've done in a group, and make it in details, as detailed as possible. Then we will know what you've done and how much work you've done in your group already, something like this. All right, so any other questions on the group project?
Does this also include, like, what kind of ROS packages you found online, or what ideas you've come up on, what kind of what you want the robot to do or something? Does that count in the mid-review report, or?
Yes, it is really counted. So, but what I mean is, by writing the mid-review report, it is required that it is only by your part, which means suppose you are working on the control of the robot, right? Then what's your thinking? What's your thinking of the problem, and what's your like methodology or strategies about doing that, and what kind of methods you've done. I don't um, I don't expect you to copy and paste codes.
Hmm.
You really want to submit some partial codes of your work, then you can submit it separately. But it is better to write your code as an algorithm into the report, because later you will submit your code as a complete one in a group, right? So I definitely know that code is not that 100% ready for the full project, but may only work on your own task in it. But what I mean is write the code and your work in detail, as detailed as possible, and write the code into algorithm in the report instead of just copying and pasting your code into the report.
Hmm. Could we also like put like screenshots of our progress like on Linux or something onto the document, or?
I do suggest you to make the screenshot of the code or the command window.
The
But if you do have something, for example, you are designing the simulation environment and you are doing some experiments in the simulator, and definitely you need to do some screen coding, screen copy, and put it as some figures of your experiments or your work.
Hmm.
Yeah, but not the codes, not the command window, please.
Hmm.
Yeah.
Right.
Cool, thanks. So any other questions about the review report and also the project? All right, so if all good, let's go to today's lecture. Yeah, so I do believe you've watched the video recorded in last semester already on the ETS Online. So in the lecture again, so we will only go for some important things instead of like repeating a complete lecture. Then we'll finish all the sensor part. So hope you've enjoyed that. And before we start doing on the control part, and we also give a feature extraction and checking session. So that is also quite important because you are not directly using a complete image to the image, but instead you always get some features from it, which contains most of the information you want. Then you can use it. You can use the features and can check them and to apply it into your work. Right? For example, if you want to do a 3D triangulation from a stereo camera, then you do have to do the feature extraction from each of the image and then do the feature matching, right? And also, when you do this kind of matching or checking, there are a lot of outliers in it. So, which means wrong matches in it. So how to delete or remove those outliers, then we introduce a very, very famous method called RANSAC. So which means you randomly select a set of the data and calculate something and to test all the rest of the data to see if they are in your threshold or not, and count the numbers, how many pairs of matches in your threshold. Then you do this kind of random process multiple times, maybe thousands or 10,000 of times. And then after that, you find a run with the maximum number of the features in your threshold. Then the features in your threshold in that run are the outlier, are the inliers, and the rest of the matches are the outliers. All right, so we've introduced different methods about the feature extraction and matching, and also we introduced the way of removing the outliers, especially for the feature matching case. All right, so that is all for the for the sensor session. Then after that, from today, we are moving to the control part. Moving to the control part. The control part is a little bit boring because there are a lot of math and in the in the handout activities, you are not working on real sensors, but instead you are working on some algorithms about the control. For example, you're formulating a problem into a control problem, a real problem into a control problem, and try to use some functions or some packages to solve this kind of problem. Right. So in the lectures, we will have 3 lectures about control. The first lecture, which is the lecture today, is about a very basic and simple case, which is linear continuous time control system. So linear continuous time control system. And in the next lecture, we will introduce still linear system, but it is discrete time system, which is more common in the real case if the problem is discrete instead of continuous time system. And after that, the last lecture of the control is nonlinear discrete time system. It is still discrete time system, but it's nonlinear, which is more close to the real case, because in a real case, most of the things are nonlinear instead of linear. All right, but the things is a bit complicated. So why we start with linear continuous time system is it nearly contains all the basic things of the control. And after you have the linear continuous time system, then when you have linear discrete time system, you have a better comparison between them. And some of the ideas are based on the knowledge you have on the linear continuous time system. All right, and also the linear continuous time system can be converted into discrete time system. All right, and after that, when we introduce the nonlinear discrete time system, it's also based on the knowledge you have in the first 2, which is the linear discrete and linear continuous time system. Because nonlinear system is quite complicated, so everything we analyze on that system is on the equilibrium point, on a certain point. We call it equilibrium point. We will show you in the next 2 lectures. Then on that point, then we can linearize it. Then we can evaluate the properties of an honor control on that point, but not the complete system because it's so complicated. And after the 3 lectures about control, we will also introduce one lecture, which is about the combination of the control and the sensing, which is a very typical and traditional and very, very useful problem, which is visual servering. So if you are working on the project about visual servering, I do suggest you to have a look at the lecture notes and the record on that lecture. All right. So after the 3 lectures about control, we will have a visual servering lecture, which is a combination of the sensing and control. Which means you have a sensor. You mount it onto a robot. Then you want to control the robot with the information get from the sensor. So that is the visual servering, and we will introduce a very traditional way of solving that problem. All right, so that is a general idea about the lectures in the next couple of weeks. Then let's go to today's one, which is linear continuous time system. All right, so before we introduce the linear continuous time system, let's introduce what is a control system. All right, so and here is a figure. Here is a figure about a control system. So we have an input and we have output. All right, then we have our control low, then to a controlled system. Right, so a control system is something like that. The objective of the control low, of this control low, is to manipulate on one or more of the system inputs to achieve the desired outputs. So which means we are designing a controller of a system, of a control system, to manipulate on the inputs, then to get the desired output. All right, and sometimes because for the system we have some noise in it, right? So you can't make it as the desired one. You have some noise in it. Then what we always do is we use a sensor. We use a sensor to detect the output from the system, and then as a feedback to the controller. Then we can use this feedback to adjust our controller and then adjust the input to make the desired output. And in this case, we call it closed loop control system. Closed loop control system. And in this, in the later of this lecture, we will show you the very simple case, which is the state feedback control. State feedback control. All right, so that is a control system. And today and the rest, we are using the state space model for the control. State space model for the control. All right. So if your control system is linear and continuous time system, then we can model the system as a state space model like this, right? So that is x dot is equal to ax plus du, and y is equal to cx plus du. And here the x is the state. The x is the state. We want to monitoring the change of the state. That is the state. It can be a vector. It can be a vector instead of a scalar. It can be a vector. Then the u is your input. Your is the input. The u is the input. All right. And y is the output. Y is the output. All right. So in this case, you can see the x, y, and u are the functions of time. So which means if time change, the x, y, and u will change. And in this case, they are continuous. So all x, y, and u are continuous with respect to time. All right. And then if the system is linear, then which means x dot, which means the change of the state x with respect to time, is a linear function of the state x and the input u. All right, and the output y is also a linear function of the state x and the input u. All right. All right, so that is the linear continuous time state space system or state space model. All right, so the x dot means the derivative of x with respect to time. Right, so if your state x is a function with respect to time, then x1 dot is the derivative, is the first order derivative of x, state x, with respect to time. It represents the change of the state x with respect to time. All right, so this is the standard formulation of the linear continuous time system. And again, because it is linear, you can calculate the derivative. If it's not linear, you can't calculate the derivative, right? Sorry, if it's not continuous, you can't calculate the derivative. So in this case, it is continuous. So which means you can calculate x dot. So the x dot is equal to ax plus bu, which means x dot is a linear function of x and u. And the y, which is the output of the system, is equal to cx plus du, which means the output y is also a linear function of x and u. All right, so this, do remember, this is the standard formulation of the linear continuous time system. And here we also have an xt0 is x0, so which means that is the initial state. So for example, if you consider a system and you can consider a starting time as the initial state of the system, and then that is it. All right, then why we use state-space model? Why we use state-space model? So there are three main advantages of the state-space model. Right. The first one is it naturally comes from many physical systems. I'm going to show you about this a little bit later. So which means if you have a real problem and how to formulate the state-space model is from their physical system. All right, so that is the first advantage. Then the second one is it's easy to deal with multi-variable case. I'm also going to show you about this advantage a little bit later in this lecture. All right. So again, it is easy to deal with multi-variable case, which means your state x can be a scalar and can also be a vector, and the vector can include multiple variables, right? So that is in the state-space model we introduced. It is easy to deal with multiple variables. You can just put it into a column vector for your state. All right. And the third one is it is also suitable for studying nonlinear models. I can't show you today, but I will show you about this point in the lecture after next. All right, so we'll introduce the nonlinear discrete time system. All right, so those are the three advantages of using state-space model, and then let's go to a real case. Let's starting with a real case. Let's see what this real case and how we can formulate this real case into the state-space model. All right, so how to formulate it with the standard formulation of the controls linear continuous time system control for this real problem. All right, so this problem we call it simplified jacking control, or we call it cruise control, simplified cruise control. So which means suppose you have a car, the mass is m for that, and you have a force U to jack the car, and then there is a friction. There's a friction of the car on the opposite direction of the force you gave, right? Of the force you gave, and we'd like to formulate this dragging control or cruise control problem into the state-space model by using mathematics. All right, and the input in this model is the force you gave to jack the car, which is U, and the output is V. So we want to get the output of V, then we know what is the speed of the car and want to make some control on the speed. Right? So this is a real problem, and I think it's quite close to you because if you drive a car, you know a lot of cars have the cruise control system, and this is a very basic version about the cruise control. All right, so what we can do is, as I mentioned before, this is from the formulation of the control system itself comes from the physical system. So here we use the Newton's second law. Newton's second law. All right. So the sum of the force of the car has is equal to m times the acceleration. Is that right? That's from the Newton's second law, right? That's the physical meaning of this system. All right, then let's see what we have for the sum of the force. The sum of the force is first the input force U minus the friction, right? And also the friction is a linear function of the speed, right? Then we can write the sum of the force the car has is U minus BV. V is the speed of the car. All right. All right. So that's the sum of the force, and that is equal to m, the mass, times the acceleration. And as we know, the acceleration is the derivative of the speed with respect to time, right? Then we can write the acceleration is equal to v dot. Is that right? Then we can write v dot here. So this is the physical formulation of the system from the Newton's second law. All right. Then we can transform that equation into this by dividing the m on both sides of the equation. Then we have this, right? Then that is the standard formulation of the linear continuous time system, right? Then you have formulated the system already, right? This is v dot is equal to minus b divided by u times v plus 1 divided by m times u. So u is the input, and v is x, is your state. Then the v dot is equal to this. And also your output is y, right? And output is just the speed. What we want is the output is speed. Then we have y equal to v. All right. Then for the standard formulation, you have a equal to this, b equal to this, c equal to 1, and d equal to 0. And then you have formulated this jogging control or the cruise control system into the linear continuous time system. Right? Is that right? Is there any questions about this? Is there any questions about this? Okay, so if everything's fine, then I'd like to show you an example about this cruise control system. So this is what we get from that system, right? Then we suppose m is equal to 100 and b is equal to 80. Then if we want to make the force is constantly equal to 1,000, then there are some MATLAB functions then to help you to formulate that problem. Then when we run the code, then you can see something, right? So the first figure is about the input. The input is the force. Then we constantly making it as 1,000, and the x-axis is the time. All right. Then this figure shows the state. What's the state in this case? The state is the velocity, right? The state is velocity. So the velocity of speed. The speed is the state. Then you can see here. So at the beginning, it starts from 0. The speed starts from 0, and getting faster, faster, and faster. Then when it reached a certain speed, then the speed will keep constant. All right, so that's the property. That's the property of this cruise control system. And the output is also the speed. So that is the figure 2 and figure 2 are the same, and the figure 3 are the same. All right. So if you want to, so in this cruise control system, after you formulate it into the state space model, then you can analyze the properties of this system, of this control system. Right. For example, the system is about to make a constant velocity later, and always reach to that, right? And if you want to change the velocity it can reach, then you need to change the input, right? Then you can pass on the code. You can pass on the code on that. All right, so this is a very good, simple but very good example. Very good example about and about formulating the real control system, the real problem into the state-space model, into the linear continuous time system. All right, and as you can see, that's the one of the advantages, which means if you want to formulate the problem, then you can start with the physical system. So in this case, we use the Newton's second law. All right, so that is example 1. Then let's go to example 2. Let's go to example 2. Example 2 is the mass string damper system, which means here is a mass, which is M, and here's a string, and here's a damper B. And we use a force F to push the mass. All right. So in this case, we can also, wait a minute. In this case, we can also use the Newton's second law. And then the sum of the force is the F, the force we pushed, minus the force from the spring. The force from the spring is K times X. X is the position, right? Position of the mass, right? It's the K times X. And also minus the damper, the force from the damper. So which is also B times F, right? So that is sum of the force. That's the sum of the force. And also it is equal to the mass M times the acceleration. All right. So after we have this, So after we have this, then we can write the Newton's second law, right? So that is the F minus Kx, x is the distance, minus Kx minus C or B x dot, which is the x dot, which is the speed of the m of the mass, then is equal to m times x2 dot. So here we use x dot, and x2 dot. So if x is the position, then what is x dot? The x dot is the velocity, right? So the first order derivative of the position with respect to time is velocity. And what is x2 dot here? And the x2 dot is the first order derivative of the speed of x dot with respect to time, which is the acceleration, right? That is also the second order derivative of the x with respect to time. That is also the acceleration. And from the Newton's second law, we have this formulation. Right, then we have this formulation. Then you can see there's x2 dot and x dot and x here. How to write it into the standard formulation? standard formulation of the linear continuous time system. Because in the linear continuous time system, we only have x1 dot, not x2 dots, right? We only have x1 dot. But here we have x dot, x2 dots. How can we rewrite it into the linear continuous time system? So that is the second advantage I mentioned before. So if you consider your x, wait a minute. If you consider your state x combining with two variables, the first variable is x, which is the position, and the second variable is x dot, which is the velocity, then you can rewrite the system into the standard formulation of the linear continuous time system. That is, capital X dot is equal to AX plus BF, right? And your A is something like this, and your B is something like this. Why is that? Because when you define your X into X and X dot, then what is your X dot? The capital X dot. X dot is equal to X lowercase x dot and x2 dot, right? Then in this case, right, you have x2 dots here. You have x2 dots here already, right? So that is another advantage of using this model, because when you have x2 dot, x dot, and x together in this case, then you can simply make your state vector with multiple variables. Then you can also formulate this into a standard formulation of the linear continuous time system. All right. Let me check if I have an example about that. This is the one. This is the one. So this is what we formulated from the max spring damper system, right? And when we run it, then you can see. Wait a minute. All right, then you can see what the system will look like. And this is input. So we still constantly make our force F as 50 as a constant input. Then we can see our state. Where's our state? So here's our state. So in our state, we have x. We have our x and x dot, right? Which means we have a position and also the velocity. And you can see the red one is the change of the position during the time. During the time changes, so you can see the position will change something like that. Then the black one, so the black one is the x dot, which means the velocity of the mass. And you can see it's still changed like that during the time. And the output is the position, so which means the output is something like this. Right, so it's quite interesting, right? So you have physical system, and then you can formulate the physical system into the state-space model linear continuous time system. You can formulate the real problem into a control system, and then after you formulate that, then you can see the properties of that control system. Right? You can analyze the control system by formulating the real problem into the linear continuous time system, and then you can do a lot of tests on that, and you can see what the output and what the state will change during the time, and you can also change the input to see what will change for the output and for the state. Right, so those two are the I believe they are simple examples simple examples of linear continuous time system control. All right. So we do have some complicated ones, but I don't think I'm going to show you in the lecture. So maybe in the handout activities, then Malin will work with you on those things as well. And also, I've put the formulation. I put the formulation already for the inverse pendulum. Then you can try to formulate it and also try to play with it by yourself. All right, then there are also a lot of interesting examples online. So, then you can. So I put the link there. Then you can have a look. So this is the link about different examples of the control system, and also it has the codes and also the data already in the MATLAB and Simulink. For example, the cruise control, the motor speed, and also the motor position or something else. All right. So if you are interested in the examples, and that is a very good link to see, and there are codes and very detailed tutorial in it, then you can have a look. All right. All right. So after we introduced the linear continuous time system, and also we introduced how to formulate the real problems into the linear continuous time system, then you can see what it will change after you formulate the problem. Right? So what's the output and what the state will change. Then that's introducing a definition about a solution. The solution to the state-space model. So what is the solution to the state-space model? So the solution is that if you have a solution, and also you have your input and also your initial state, then you can calculate the state at any single time step, at any single time. All right, so that is why we can show you how the state or how the output will change during the time, right? So that is from the solution. So the solution of the state-space model, or the solution to the linear continuous time system, means from the solution, if you have initial state, then you can calculate the state at any time. That is the solution. And for the linear continuous time system, the solution is like this. The solution is like this. All right, so you don't have to derive on that. Then you just need to remember that, and then when suppose there is a question in the quiz 2 or in the final exam, I'm asking, what is the solution for that control system? Then you need to find this equation, write it down, and replace A and B by the real ones, by the real numbers or real matrices, and that's it. All right, and also I've already shows you about this about this solution. Right, so when you have the system formulated already, then you have an initial state, then it can calculate the change of the state, also the change of the output at any time. I'll show you about it already. All right, so that is the solution. So the meaning of the solution again is from the solution, if you have an initial state, then at any time step, you can calculate the state. You know what is the state. All right, so that is the solution. And I think I've shown you already about this, about those solutions, right? So this is the cruise control system, right? The cruise control system. And also I've showed you the mass spring and damper system already about this. And then we will introduce the definition of the stability. All right. So the stability, the definition of the stability is that if you have a linear continuous time system, the system is called asymptotically stable, or simply we call it stable, if for any initial state, the state x will converge to 0 when the t increase. All right, so let me repeat it again. So if a system is stable, if a control system is stable, that means for any initial state, the state x will converge to 0 when the time increase. All right, so when the time increase, the state will definitely change during time, right? So the state will converge to 0 during the time increase. That is called stable. That is called stable. All right, so here I give a very simple example. So the example 1 is x dot is equal to minus x. All right, and another example is x dot is equal to x. And the solution is quite simple as well. That is solution, and that is also solution for example 2. And let's see what the state will change for the 2 different problems. All right, so sorry about this. One dimensional stability. Okay, so suppose we have x dot is equal to minus, sorry, the 0.1x, right? So which is a is equal to 0.1. Right, and let's see what the wait a minute. So let's see what the state looks like. All right, so as you can see, when the a is equal to 0.1, so which means in the problem, the x dot is equal to 0.1x. And in this case, you can see the state will come larger and larger and larger and larger and larger and larger. And tell me if it is stable or not. It's definitely not, right? Because in the definition of stable, so if the state will change towards 0 when the time increase, then that is a stable one. So this one is definitely not, right? Then if we change, sorry, wait a minute. If we change problem from x dot equal to 0.1 to x dot equal to minus 0.1, which means a is equal to minus 0.1. Let's see what will happen. And in this case, you can see, the state will change from a number and all the way converging to 0, right? So in this case, which means is this system is stable. And let's come back to the slides. All right, so we've checked that already. For example 1, it is stable, and example 2, it is not stable. Then we want to know, so we can see that, right? But we want to know, is there any way that we can check if the system is stable or not? Is there any way that we can check if the system is stable or not? The answer is yes. All right, so the condition of the stability is that if all the eigenvalues of the matrix A has negative real parts, or negative or has negative real parts, then the system is stable. All right, so there are 3 information 3 points of information including in this condition. First is the stability only depends on the matrix A, not B, C, and D. Right? So I mean the standard formulation of it. Right. So the stability of the system only depends on the matrix A. All right. So that's the first information. And the second information is the stability only depends on the eigenvalues of A. So when you want to check the stability of a system, get the matrix A out, nothing else, then calculate the eigenvalues of matrix A. All right. And the third information is if all the eigenvalues are negative or have negative real parts, then that is stable. Then which means suppose A is a 2 by 2 matrix, then you have 2 eigenvalues, and A has 2 eigenvalues. One is -2, the other is +3. In this case, the system is not stable because if it is stable only if all the eigenvalues of matrix A are negative or have negative real parts. For example, in this case, you have A that is -2, 0, 0, -3. And in this case, the eigenvalue is -2 and -3. And in this case, it is stable. All right. So if any of the eigenvalue is not negative, then which means it is not stable. That clear? That clear? So this is condition of the stability. And again, this is quite important. And also again, so the condition of the stability, the criteria of the stability for the linear continuous time system is different from the linear discrete time system when I introduced in the next section, but whatever. So have the idea about what's the stability of the linear continuous time system and what's the criteria, which means how to test if the system is stable or not. All right, so if the system the state can converge to 0 when the time increasing, then that is stable. Right? And how to test it is you just get the matrix A out, nothing about B, C, and D, just A, and calculate the eigenvalues of A. And if all the eigenvalues are negative, then which means the system is stable. The system is stable. All right. So that's the stability. We do have a lot of examples. I think I've already put the code onto the class online, and also in the handout activity you can play on those kind of things. All right. So about calculating the eigenvalues. The easiest way is if you're using a MATLAB and there's a function to calculate the eigenvalues of a matrix, then you do have to calculate it by hand. But if you want to calculate it by hand, if you really want to calculate it by hand, then you can use this. But because in this semester and the coming ones, we will have all examples and quiz 2 online, then you are able to use MATLAB to help you to calculate the eigenvalues, which means you do have to calculate by hand. You need to know how to calculate the eigenvalues of a matrix by using some functions in MATLAB or in C or C++ something. All right, so we also have another example about Pendulum. I have the code, and I think Malin will play with you as well on this example. I'm not going to show you how to derive those kind of things, but I'm going to show you a little bit later about if the system is stable or not and how to deal with that. All right. Then pole placement. Then the next thing is about pole placement. So suppose you have a system. Suppose you have a system x dot is equal to ax plus bu. Then when you check the stability of that system, which means you check the eigenvalues of A and you find one or some of the eigenvalues are not negative, which means the system is not stable. But you want to make your control system stable, right? So this is what we always want to. We want to have our system to be controlled that is stable, right? Then what we can do for that? So if you have a linear continuous time system, and you check that it is not stable, and what we can do. All right. So one of the way is the pole placement. We call it pole placement. And here we use the state feedback control. So this is what I mentioned before. So if you can observe the state, and that is the feedback by using some sensors, then that's the feedback to control law. And we use the state feedback control. That is your input u is equal to minus kx. So suppose we have some sensor which can observe your state. Then we can change the input. We can change the input as minus kx, which is a linear function of the state, right? Then the original problem x dot is equal to ax plus bu will be changed into ax minus bkx, right? Then we can write it into this, right? Then when we use the state feedback control, then the original problem is changed into x dot equal to a minus bkx, right? And as you can see, this is your new A matrix. Is that right? This is your new A matrix. Your matrix for the state feedback control system. Your original problem is changed into this. Then your original A matrix changed into this. So your new A matrix is equal to A minus BK, right? Then for most of the cases, A and B are constant. Then you can choose the K, right? So you can choose a proper K. You can choose a proper K to make the new A matrix, which is A minus BK, has all negative real parts. Sorry, all negative eigenvalues or negative real parts of eigenvalues. Which means if you choose a proper K, for the state feedback control system, then you can make the system stable, right? So that is the pole placement. And then that's giving an example. So for example, if we have an A matrix like that and B matrix like this, right? Then as we can see, the eigenvalue of A is -3 and 1. So we have A has one eigenvalue which is not negative, which means the system is not stable, right? Then if we choose K is equal to K1 and K2, then if we use the state feedback control, then the new A matrix for the state feedback control system is A minus BK, then it is something like this. It is something like this, right? It is something like this. Then if we choose K1 equal to 0 and K2 equal to 2, then we have this new A matrix, and we can see this A matrix has eigenvalue -3 and -1, and then this closed loop control system is stable, right? So which means if you use state feedback control, then you have A minus BK. Then if you choose proper K, then you can make your system stable. You can make the closed loop system stable. All right, so that is the pole placement. I think I do have some example, and then I think I'm going to show you a little bit later. Yeah, a little bit later. All right. So that is a pole placement. The pole placement means if you have a system and the system is not stable, you check the system is not stable, then you can use the state feedback control and then to make the new system as x dot equal to a minus bkx. Then the new A matrix for the state feedback control system is a minus bk. Then you choose some proper k to make a minus bk has all negative eigenvalues, then which means you make the state feedback control system stable, right? So that is pole placement. Then the question comes to, are all the systems which are not stable, we can use pole placement to make it stable? The question is, so can we use the pole placement to every system that is not stable? The answer is no. So the pole placement cannot be applied to every system. Then how we can check if a system can use this pole placement to make it stable? Then we called it the system controllability. All right. So if you have a system and that system is not stable and you want to change the system by using the state feedback control to make it stable, then you have to check the controllability. So if the system is controllable, then you can use pole placement to make it stable. Otherwise, you can't. And here we introduce how to check the controllability. And if you remember, for the stability, it only depends on the matrix A, right? But for the controllability, it only depends on both matrix A and B. All right. So suppose we have a linear continuous time system, which is x dot is equal to ax plus bu. Then we can calculate this controllability matrix, which is b, ab, a squared b, so a power 2b, a power 3b, a power n minus 1b. All right. So we can calculate this controllability matrix. And if this matrix has 4-row rank, then that is stable. All right. So which means if we have a state-space model or linear continuous time system, that system is completely controllable if and only if the controllability matrix has 4-row rank. I will using the following 2 examples to show you how to check the controllability. So this is the first one. So suppose we have a system with matrix A -3, 1, -2, 0, and have the matrix B 1 and -1. I suppose you have this control system. And how to check the controllability is you first calculate the controllability matrix, which is BAB if the dimension of A is 2 by 2. If it's 3 by 3, then you have to have another column. Right, so if A is 2 by 2, then you need to only calculate B and AB. The 2 columns, right? Then if the matrix of A is 3 by 3, then you may need to calculate B, AB, and A squared B, something like this. All right. Then in this case, we can calculate the controllability matrix, which is B and AB. Then the first column is B, right, which is this. The second column is A times B, which is -4, -2. Then we have the controllability matrix. Then the next thing is to check if the system, to check if the matrix has 4-row rank or not. To check the rank of the matrix, the controllability matrix. And so what we can do, we can have 2 ways to check it. We can have 2 ways to check it. The first way is to calculate the determinant of the matrix. In this 2x2 case is 1 times -2 and -1 times -4. And that's the determinant of the matrix. And if the determinant of the matrix is not equal to 0, then which means the matrix is 4 rank. All right, the matrix is 4 rank. And if you want to calculate the determinant by hand, you can calculate it by this. So 1 times -2 and -4 times -1. Right, so that is if you want to calculate the determinant by hand. But a much easier way is you can just use a function, det in MATLAB. Then you can calculate the determinant. And if the determinant is not equal to 0, then which means the matrix is 4 rank. Then if the determinant is equal to 0, then which means the matrix is not 4 rank. All right. So how to check the controllability is first you get A and B, and then you calculate the controllability matrix. Then you have the matrix already, and then you check the rank of the matrix. If the matrix has 4 rank, then which means it is stable. The control system is controllable. Then you can use state feedback control, and you can use pole placement to make it stable. All right, so that is one example. Then I'm showing you another example. This is your homework. So try to check the system controllability by yourself. So if you have A and B, something like this. Then in this case, we can also calculate the controllability matrix, which is 1 and -2 and -1 and 2, right? And after that, we need to check if the matrix is 4 rank or not. And in this case, if we calculate by hand, the determinant, as we can see, that is 1 times 2 minus -2 times -1, which is equal to 0, right? So the determinant of the controllability matrix B, AB, is equal to 0, and which means it is not 4 rank. Then it is not controllable. It is not controllable. All right. Then I'm going to show you another intuitive way to see if the matrix is 4 rank or not. All right. So for example, in this matrix, let's consider the first column and the second column. Right. So if we use the first column and times -2 on that, then we can get the second column, right? Right. So if we times -2 on the first column, then we can get the second column, which means the 2 columns are not linear independent. Then which means it is not 4 rank. And also, if we can see the rows, if we times -1 on the first row, then we can get the second row. And which means the two rows of the matrix are not independent. So which means it is not full rank. So there are two ways of checking if a matrix is full rank or not. The first way is the mathematical way. You just calculate the determinant. If the determinant is not equal to 0, then that is full rank. And if the determinant is equal to 0, then that is not full rank, which means the system is not controllable, right? And another way is an intuitive way. So if one of the row or the column can be represented by the linear function of the other rows, then which means that is not full rank, then that is not controllable. All right, so that's the controllability. So which means suppose you have a system, then maybe the first thing is you can check the system if the system is controllable or not, right? If the system is stable or not. Then if it is not stable, and then you want to use a state feedback control and pole placement to make it stable, right? But before you're doing that, you need to check if the system is controllable or not. Right? Then you use this way to check if the system is controllable or not. So if it's controllable, then you can use pole placement to make the system stable. Right, so that's the whole story. But I'm going to ask you another question. As we can see, in the previous question we have, so we can choose proper case to make the system stable, right? But we can choose multiple case, which means we can choose a lot of case, which can all of them can make the system stable, right? So we can have like 2 solutions or like 10 solutions or even 100 of the case that make the system stable. So which one is the best? Which one is the best you want to use? That is the optimal control problem. That is the optimal control problem. We call it linear quadratic optimal control. All right. So the problem is solved. Here I gave an example. So if you choose different k1 equal to 2, k2 equal to 3, then the problems change like that. The state will change like that. Then if we choose different case, then the state will change different. Which one is the best? Right. So that is the linear quadratic optimal control. All right. So the definition of the linear quadratic optimal control is, suppose we have a standard formulation of the linear continuous time system, and if that system is not stable, then we use the state feedback control by making u is equal to minus kx. That is the same as what we have for the pole placement, but we want to find the optimal k such that the performance index is minimized. All right. So we have a linear continuous time system. Then we want to use the pole placement state feedback control, but we want to get the best k. And what we can do is we are trying to find the best k which can make this performance index minimized. And that is the objective of the linear quadratic optimal control. And how to do that is, here we use a Riccati equation. So we can calculate P from Riccati equation. You don't have to know how to calculate it, just know about the steps. That's fine, because there are a lot of packages or functions help you to calculate this, and you will definitely test on that in the handout activities. So in this case, we first use Riccati equation to calculate P, and from P we can calculate K, right? And from K we can calculate U, right? And we can also calculate the minimum performance index as well. So that is how to solve the linear quadratic optimal control problem. So we still want to use the state feedback control, which is u equal to minus kx, to make the original linear continuous time system stable. And what we want to do is we want to choose a proper k that minimize the performance index, minimize this performance index. And what we can do is we first use Riccati equation to calculate P matrix P, and from matrix P we can calculate the k, and from the k we can calculate u. Right? And we can also calculate the minimum performance index. So that is the linear quadratic optimum control. All right, so that is, so we have some examples, but I'm not going to show you today, and I do believe Malin will be with you to work on those examples. All right, so for a summary, today we introduced the linear continuous time system. That is the very basic, very simple case of it. And after that, we will introduce linear discrete time system and also nonlinear discrete time system in the next two lectures. And we introduced the standard formulation of the linear continuous time system, and we try to use some examples to let you know how to formulate a real problem into the control system, into the linear continuous time control system. And then after that, we introduce the solution of the control system, which means from the solution, you can calculate the state at any time. That is the solution, right? And we also introduced the stability of the system. And the stability means if the state will converge to 0 when the time increase, then which means the system is stable. All right, so that's the definition of the stability. And how to check if the system is stable or not is the stability only depends on the matrix A, nothing else, only depends on the matrix A. And then you calculate all the eigenvalues of matrix A. Then if all the eigenvalues are negative or have negative real parts, then which means the system is stable, right? That's the ideal case. The system is stable, just control it. You want to control the system as stable one, right? But if the problem is, if the system is not stable, what we can do is what we call it is the pole placement. So we use the state feedback control, which means we change, suppose we have a sensor which can observe the state. Then we can change our input as the state, right? So we can change our input u is equal to minus kx. Then we can choose a proper k to make the new A matrix, A minus bx, has all the eigenvalues are negative, right? So when we use state feedback control, when we choose u is equal to minus kx, then the new A is A minus bk of the system. And then if we choose a proper k, then we can use all the eigenvalues of this matrix negative, right? Then which means in this case, then we choose proper k, then we can make the system stable, right? But the thing is, not all the system you can use pole placement to make it stable. Then what we need to do is we need to check the controllability of the system before we're using pole placement. Then when we have a system and we check this not stable, we want to make it stable. And the first thing is we are checking this controllability of the system. The controllability depends on the controllability matrix, which is a calculation from both the matrix A and B. right? And if the controllability matrix has 4 rank, then the system is controllable. Then you can use pole placement to make it stable, right? So that's the controllability of the system. Then, because for pole placement, we can really have multiple cases to make the system stable, right? So which one is the best? Then we introduce the optimal control. Then the optimal control is to choose the best K or the optimal K, which makes the performance index minimized. Then how to solve it is we can calculate P from Riccati equation, and when we have P, then we can calculate K, the optimal K, and then we can have the optimal U as well, right? And then we can calculate the minimum performance index. All right, so it's a story. It is I've introduced the definition of this control system and also some properties of it and how to check the properties, but they are connected to each other. All right, so it's a whole story about the control, and hope it is. I know it's a bit boring comparing to sensors, the sensor part, but hope you will like it because it's quite useful as well. All right, so that is all for today. And is there any question about this lecture or also anything else? Is there any questions? So, are there any questions? So, if no, thank you again for coming to this lecture, and let's move to the handout activities, Ms. Marlene. Thank you very much. See you.
Thanks, yeah. Hi, everyone. Give me a sec till I set up computer. Okay, can everyone hear me? Can everyone hear me and see my screen? Okay, thanks. Give me a sec. My computer is acting slightly weird. All right. Okay, so what we're going to do first is, so I marked all of your project proposals. So we're going to talk a little bit about that. And then I'm going to spend a little time discussing how to plan out your project a little bit better, because based off of what I saw in your project proposals, I thought it might be a bit useful for most of you to kind of learn how to break down a project and how to manage a project. So I'm going to spend a couple of minutes talking about that, specifically like how to deal with a robotics project, because there's so many bits and pieces and so many subsystems that you have to worry about. So I'll talk about how you can kind of break down a robotics project and how to kind of manage it. And then I'm going to spend the last few minutes continuing the discussion about transformations and show you a couple of cool ROS tools that will help you understand transformations a bit more. And then if you have time, I'll also show you how to not just read ROSBags from MATLAB, but how to kind of listen to, subscribe and listen to topics in real time in MATLAB. Basically, how to connect MATLAB with ROS. So far we've read ROS bags onto MATLAB, like we've loaded ROS bags into MATLAB and then looked at what's inside those ROS bags. But if your robot is working in real time, or for example, you played a ROS bag, I'll show you how to kind of listen to that in real time in MATLAB, which I think might be beneficial for your projects. And so I'm not really going to talk about controls today, because I think right now most of you are worried about your projects, and I think talking about your projects right now would be more beneficial. So just before we start, just a reminder, the full playlist of all the videos are up on YouTube. So where we are right now is tutorial 6, right? So tutorial 6 is the first tutorial in the controls section. And I suggest everyone watch these 3 videos. So they introduce controllers and then and basically covers the first question, second question, and third and fourth questions in tutorial 6. So I think next week is 2WAC. Try your best to finish this. Again, I can see the statistics on these videos because it's on my YouTube channel, and not many of you are watching these videos, which is kind of scary because it's making me slightly regret not running through every question during class and focusing on these extra stuff. But I think focusing on this extra stuff is beneficial for you, but it'll only be beneficial if you actually do the other, like the proper tutorial questions as well. So please watch these videos. Don't wait till the last minute before the exam and stuff, because each of these questions will really help you figure out your project as well, right? Because these, like, so Liang covers most of the theory sections. These questions will cover like practical ways of processing your information, doing so far we've covered half of the course, where we basically talked about how to acquire sensor information and how to process that sensor information, right? So please do these questions in these tutorials and watch these videos, because they'll help you get a better understanding of how to approach your projects, which is what we're going to really talk about today, right? So first of all, let's discuss briefly about your project proposal. So most of you did all right. So I think if you got above 4 marks, I think you're generally okay. But I saw a huge difference between the people who got 5 and everyone else, right? So I think particularly group number 5 and group number 17, I just want to give them a shout out because I thought their project proposals were excellent. They've done a really good job and put in a lot of work in kind of basically laying out the problem and then showing possible solutions. So yeah, shout out to group 17 and 5. Good job. Everyone else, all right. There were, like I said, if anyone who's gotten above 4 is generally okay, but there are quite a few things like I was personally looking for that I didn't really see in most of the proposals, which is basically a breakdown of the problem and potential ways of approaching the problem, right? Because you are right now in week 6, which means you have roughly 5 more weeks left. And the whole exercise of getting you to write the proposal was so you could plan out your project and have, obviously, I wasn't expecting you to give solutions in your proposal to most of the problems, but I think correctly identifying what the problems are. And I was also looking for potential solutions, right? You don't have to give me one solution, but just say, for example, if it's how do I detect a square, some sort of idea of what sort of approaches you could take, right? So we've already discussed, for example, Harris corner detectors, right? So if you've done the question in tutorial 4, I believe, about Harris corner detectors, you would know that you can easily detect the edges of the square. So that is one way of detecting edges in a square, right? So sort of concrete examples of the kind of approaches you could take was kind of what I was expecting from your proposal. especially in the approaches section. So most of y'all got the scope right, the deliverables all right, but the approach, basically, if you haven't caught on by now, there are mainly like two things in a robotics application that you have to worry about. It's the sensing angle and the control angle, right? So if you can have some sort of idea how to approach the sensing angle and how to approach the control angle, like I said, I'm not looking for concrete solutions or concrete answers, because those are things you have to figure out throughout the process of the project, but at least an idea of potential options, right? And that's where, like, again, I gave like 1 mark for references as well, because some of you had just referenced Liang's project proposal document. That's it. That was like the only reference in your entire proposal. And I found that to be quite like, it's that's where, like, for example, like I said, if you had multiple options of how to approach the sensing problem, you would link to the references of material you can find on that, right? So for example, if it's the Harris corner detector and SIFT that you think might be the best solution, you would reference to those papers or reference to some sort of resource that highlights that, right? Referencing Liang's document that he put on UTS online is not a reference, right? So in an academic context, a reference has to add something, right? You're kind of referencing um, basically different approaches you could take, or like the references carry weight, right? Another simple tip about writing a proposal and stuff is, and this is a very, like I gave like 0.5 marks for presentation. Right? And what I mean by presentation is not necessarily like a fancy looking, like a cover page or anything like that. Like, I don't care if it's even just a plain Word document, but simple things like typos and spelling mistakes and things like that. Like, trust me, I hate when people nitpick on those things myself. Like, for example, sometimes I would write like a conference paper or something, send it to a conference, and I've been working all night and I would make typos and mistakes, right? And I hate it when, like, I've done all this great work and people who are reviewing my paper would be like, I found a typo here, which is like, it just infuriates you and pisses you off, because it's like it's not the important part in your document, right? Like, you care about like the content of the document, not exactly about typos and stuff. But the sad reality is, like, people in the real world care about those things, and you don't know who would be looking at whatever document you've written. And also, like, if you have a lot of typos and things, it kind of makes you look bad, right? So I gave like 0.5 marks. I didn't like mark people down a lot on it, just 0.5 marks. But make sure from now on, if there are documents that you need to submit, make sure that you proofread them. If, for example, English is not your second language, which is not your first language, which is also understandable, maybe send it to someone who can proofread it for you, and make sure your document is grammatically and is correct with no typos and stuff, because it can make you look bad, right? So I didn't mark you down too harshly on that. Like, my main focus was on the actual content, whether you actually looked at that stuff. But in the real world, people do care about stupid things like spellings, right? So just as a lesson for you in the future, make sure you make your document, just check for typos. I think you can use Grammarly as well, which is a easy online website. You can just upload your document and it'll pick out all your grammar mistakes. But always have someone else to look through it, right? Someone to kind of proofread your documents. Okay, so those are the two biggest things I have to say. Basically, one, make sure your presentation is on point. Number two, make sure you pay attention to your approaches and things like that, because by this point in your timeline, you only have 5 weeks left. So there is no time to start discovering things now, right? The entire point of the proposal was for you to kind of look at what your options are. Okay, so having said that, let's kind of break down typical project and look at how best to approach it. Okay. So where is my hold on a sec. Okay, cool. Hold on, my computer has been acting a little weird. Okay, could you guys give me like 2 minutes? I think I might have to restart my computer. I'll be back. Don't leave, okay? Because today's session will be really important, especially on how to kind of structure your projects and stuff, and how to approach like a complicated robotics project, how to break it down and stuff. Just give me like 2 minutes. I'll quickly restart the computer. And I'm back. Sorry about that. I've been running all this crazy stuff on my computer, and yeah, it decided to completely crash on me. Can everyone hear me and see my screen? Okay, just to confirm.
Yes.
Okay, thanks. All right, give me a sec. Let me start recording. All right. So where were we? Okay, so we were discussing robotics. Jeez. What the heck, man? Sorry. There we go. Sorry about that. So my computer is acting completely weird today. All right, so project management. Not just regular project management, we're going to discuss how to sort of do it in the context of a robotics project. Okay, so the first thing you need to do is, the first step is break down the problem. Okay, so before I get into the details of this, just a couple of important caveats, right? Number one, everything I'm talking about is going to be very generic. So it's going to be very, very general. So it might not apply to specific instances of your project, but it's supposed to encapsulate all types of robotics projects, right? I'm just basically going to talk about the big sort of components of a typical robotics project. So it's up to you to kind of adapt it to your specific project. The second caveat is that nothing I'm going to talk about in today's lesson is written in stone, right? So this is just how I approach a problem. That doesn't mean there's only one way to do it. It doesn't mean that you need to follow everything I'm saying exactly to the nitty-gritty details that I'm going to go into. It's just one way of approaching the problem, and it's completely up to you to approach it any way you like. But this is based on my experience, right? So let's talk about a typical robotics problem. So obviously, if you're talking about a typical robotics problem, you need a robot, right? So the first component, so if you're trying to breaking down this problem, the first component that you have to think about is the robot, right? So you would have a robot. This is my general idea of a robot. And this can be either in either in hardware or it could be in simulation. Okay. I apologize if my writing is a bit weird because my computer is still acting slightly strange, but let's power through this. Right. So it could either be in hardware or simulation. Right. So the great thing about ROS is it doesn't really matter. Right. So there might be slight variations between the hardware and the simulation. So some of the robots might not completely have all the sensors and things like that. But generally, when you're talking about the final sort of topics that you'll be considering from a ROS perspective, it doesn't really matter whether it's hardware or simulation. Obviously, for you, you would obviously want to kind of play around with the hardware and actually interact with it. But other than that aspect of it, there's really no difference. I guess another small difference is the fact that you have to set up the simulation, right? And that might take some time in and of itself. But you come into a similar problem with hardware as well, which is kind of setting it up, right? So, so the first problem that you have to deal with if you're breaking down the problems is the hardware setup, right? So if it's actual physical hardware, you'll have to go interact with the robot, set it up, get it working, power it up, see what it looks like, get a feel for it. Right? If it's simulation, you have to do a similar step. I provided a PDF that helps you set up the simulations. But basically, that's the first problem, right? That you need to solve. Basically, set up the simulation or the physical hardware that you'll be working with. Okay. So this also, for example, if you're dealing with simulation, this also involves the environment, right? So it's not just the robot. So there's the robot. Plus, you need to have some sort of idea about the environment, right? So that it's going to play around with, right? So if it's a simulation, you'll have to look at, okay, if you're dealing with a turtlebot simulation, what sort of different simulated environments can I look at and things like that, right? So you get a feel for it. And then if you're actually working with physical hardware, again, you'd have to think about what sort of physical space will it be operating in, right? What sort of limitations will I be dealing with in that aspect, right? So all of that comes under this setup of the robot and its environment, right? So that's the first problem that you have to kind of deal with. Second, right, is basically you need to get information out of the robot, right? You need to get information out of the robot. So get info out of the robot, right? So that's going to be your second problem, right? So again, ROS makes this pretty easy. You can do this using subscribers. You can listen, right? Listen to the topics that you want. You look at what sort of information is this robot publishing, right? And you can use subscribers to get information out of the robot, right? Which is the second big problem that you have to kind of solve, right? Once you set up the simulation, once you set up your hardware, look at what sort of information is being given out by the robot sensors, right? And try and get that information out of the robot. First, you would try to do that using the terminal, or then you try to do that using MATLAB or whatever software that you'll be using to kind of do everything, right? And once you get this information out, and this is sort of the big chunk of where you'd be spending a lot of your time, it will be basically processing that information, right? Processing information, right? So once you get the information out of the robot, you have to process that information. So when I'm talking about processing information, there are two aspects to this, right? First, you need to, what do you call it? Sort of extract features or sort of, yeah, first you have to process the sensor information, right? Or yeah, let's call it processing sensor information. And then once you process the sensor information, you have to make decisions, right? So make decisions, right? So once you process the sensor information, you have to make decisions. And instead of calling this processing info, I just call that just processing, right? So there's two aspects to the whole processing. One is decision making and processing the sense information, right? So this is where you'll be spending most of your time, right? This is the big problem that you have to solve. Basically, once you get this information out of the robot, you'll have to process that sense of information. For example, you'll have to identify features, right? Figure out, for example, some of you are grasping a can, right? Like how do you recognize the can, or how do you recognize an object? Or if you're working with a project where it's two turtle bots following each other, based on a QR code or something like that, like how do you identify the QR code? That is processing the sensor information that you just got out of the robot. Once you do that, you have to kind of decide, okay, once I process that information, how am I going to, what should I do with it, right? And that's the decision-making process, right? Once you make that decision, right, you need to get the robot to do stuff, right? So we call that get the robot to do stuff that you want to do, right? So that will be, I'm going to call that the third problem, right? What I mean by that is basically once you make a decision, let's take a simple example. If it's one robot following another robot, you got the information from a camera, right? You identified the second robot that you're trying to follow. You made a decision, okay, I need to move forward. And then now you have to transfer that information to back to the robot saying, okay, I want the robot to actually move forward, for example, right? And this can be done using a publisher, right? So this is assuming you'll be using ROS, right? So for you to get information back to the robot and tell the robot to do stuff, that's where you use ROS publishers, right? So the reason I called I didn't call this big block in the middle number 3 and I looked at this as number 3 is because the whole idea here is that you want to do all of these in a modular way, right? You want to first set up the robot and its environment separate to any of the things that you're doing here, right? So getting the information out of the robot, for example, has nothing to do with how you're going to process that information. Even, for example, getting the robot to do stuff doesn't, you can do that independently of actually the decision that you make, right? So what I mean by that is, even before doing this big red block here, see if you can publish information back into your simulation, right? So you can hard code values. For example, if you can tell the robot, okay, move forward, right? Move forward 5 meters or something like that, right? And then hard code that value, see if you can publish that back into your simulation, back into your robot and get it to move 5 meters forward, right? So that has nothing to do with this block in the middle. So try to do all of these as separate, independent modules, right? So I'm just going to put these in squares to kind of emphasize the fact that these are like separate modules, right? The advantage of kind of breaking it down into these separate modules is you bite off only one chunk of the problem at a time, right? Without approaching all of it at the same time, which can be quite difficult, right? So getting the robot to do stuff, you publish some sort of hard-coded values and see if you can move the robot. For example, if it's a robot arm, see if you can move the robot arm into places that you want it to move, right? So that once you decide where to move, you can just use that same pipeline that you just created to do it, right? So these modules 1, 2, and 3 is what you would do first, right? You would try to get set up the simulation, get information out of the simulation, and see if you can publish information back to the simulation, right? Or the hardware. Okay, so these first 3 are basically what you have to do really quickly and get that out of the way as quickly as possible, right? And these 3 parts will generally be the easiest part of your project, right? But remember, the bulk of your project will be spent in this part, right? Basically, how you're going to process that sense information. And once you process that sense information, how do you make decisions based off of that sense information? That is whether to move forward, whether to move backward, and whether to move the arm forward to the side or whatever, right? So that once you made that decision, all you have to do is just connect it to this module. And since you've already figured out this module, everything will work smoothly, right? So that's kind of the hope, right? So this part is where you will be focusing on a lot in your project, and give yourself enough time to do this part, right? Because that's where your contribution is. But these other sub modules 1, 2, and 3, you need to get out of the way as soon as possible, right? So get that done like this week. Just see if you can get information out and process it, right? So to kind of help you get information out, you can use, okay, so before moving there, right, let's talk a little bit about this block number 4, right? Processing sense information and making decisions. So there's multiple ways you can approach this. You can do this in MATLAB, right? You can do this in C++ or Python, right? You can basically, either way, you'll be using ROS, right? So if you're using MATLAB, for example, when you're subscribing into information and listening to information coming from the robot, you'll have to kind of get that information to MATLAB, right? So there's a small sub problem associated here. I'm just going to call it 2.5, which is connecting to MATLAB, right? Connecting ROS to MATLAB. And similarly in here as well, right? You have the same problem, right? But once you connect everything to MATLAB, it's kind of two sides of the same coin, right? Once you connect everything to MATLAB, you can then publish back into ROS or subscribe from ROS, right? So connecting to MATLAB helps you get information out of the robot so that you can do this processing part, right? So that you can load it onto MATLAB and then kind of process it. Again, you don't have to do that. You can use C++ or Python if you want to, but since most of what we've been doing in these tutorials are MATLAB, there's nothing wrong with using MATLAB to do this as well. Right? So for most of your projects, MATLAB will be the easiest way to do this, because if not, there's an additional learning curve to deal with when you're dealing with C++ or Python, right? Because you have to kind of learn the basics of that as well. But since you kind of invested your time in MATLAB right now, there's nothing wrong with dealing with MATLAB. And since you're here to learn robotics and not to learn a programming language, I even urge you to consider using MATLAB, because you can visualize things very easily. You can debug things very easily, and it'll be slightly slower than C++ or Python. But trust me, you have only 5 to 6 weeks. So go with the easy option right now. Okay. So just a couple of important terminology, right? So getting information out of the robot and processing that sensor information. Use a different color. Yeah. So this bit that I've drawn in blue, right? This is what we call the perception problem in robotics, right? So you're trying to perceive things coming from sensor information, right? So you first need to extract that sensor information, get that information out of the robot, and then process that sensor information so you can kind of extract features and things like that, right? So everything that we did so far in our class, right, come under this perception problem, right? So everything that we discussed in sensors so far, right, about cameras, about LiDARs, all of that come under here, right? And we talked about different ways we can extract features, right? We talked about SIFT, right? We talked about Harris corner detectors, right? Convolution, all that stuff come under this section, right? Which is basically, once you get the information, how do you process that sensor information to kind of get the things that you want to look at in your application, right? Then you have the decision making part, and once you make the decisions and kind of the part where you're trying to get the robot to do things, right? So that's where the control aspect of this comes into play, right? So once you make the decisions and you want to get the robot to do stuff, that's where the control aspect comes. And so when you're talking about control, so we haven't really looked at control much yet in the course, but you don't have to worry too much because most of the robots that you'll be working with, for example, the Turtlebot, the Fetch, right? Most of them come with control packages already pre-installed, right? So for example, let's say you want to move 5 meters, you don't have to design a controller from scratch, right? Because the Turtlebots and Fetch packages already have easy to use control packages inbuilt, right? But that doesn't mean that you always have to use them. For example, if you want to, you can design your own controller from scratch. And I think some of the projects that's mandatory. Like for example, I think there is one project where you're supposed to control a handheld RGBD camera or something like that, right? So in situations like that, basically the control aspect is it's important that you build it from scratch in projects like that, right? But identify what your main target in your project is in terms of control, right? So for example, you can use these packages like move it and so on to easily control your robot. For example, all you'll have to do in some cases would say move 5 meters and it will move 5 meters and it'll do all the complicated controlling bits underneath the hood, right? But what's great about most of these packages is that if you want to implement it with like from scratch, you can still do that as well. Right? So you have access to, for example, if it's a robotic arm in the Fetch robot, you have access to all the joints in the robot arm, for example. So if you want to go and create a low-level controller that works from scratch and you want to design a controller, that option is also available to you. But in most cases, if you're dealing with a Turtlebot or the Fetch, you can very easily just pass on commands and it will do them, right? But again, there's a small learning curve there, so try to, and that's this part, right? The number 3 block. Try to look into that as soon as possible and see what sort of options you have to actually control your robot, and try and implement them. Again, implement them in a modular way so they're disconnected from, like, you don't have to complete number 4 to go to number 3, right? You can do number 3 by just hard coding values and seeing what your robot does, right? So yeah, so you have the option of designing a controller yourself or using the controllers that come kind of inbuilt with most of these ROS packages, right? But generally, designing a controller from scratch is a very, very difficult thing to do. And if you have a unless that's your project itself, which is the case in I think 2 or 3 of the projects, I would suggest just using the inbuilt controllers, right? Because tuning them and designing them is generally quite a difficult task and can be a project in and of itself, right? So the reason why we teach you the control section in this course is so that when you look at those controllers that other people have implemented, you can understand how they kind of work, and then you can tune them to kind of match your own application, or you can write your own controller from scratch if if you have some free time and that's what you want to do, right? But yeah, so break down the problem like this. So what I was really looking in your proposals was like, what are the solutions you have for this part, right? Like the perception problem, like how are you going to detect like different features, like what are the features you need to detect, things like that, right? And then once you make the decision, the second part I was looking in your approaches were like, what are your control strategies, right? Are you going to implement a controller from scratch? Are you going to use the inbuilt kind of packages, or like what are your approaches? And some of you had answered those really well. Some of you had just not mentioned anything with regard to any of these problems, right? So before we move on, any questions regarding this, right? So the idea here is to kind of break down this into mini problems, and even this processing block, right? Even this processing block, you try to kind of break it down into a set of smaller problems, right? break it down into a set of smaller problems, and before moving on to a problem, make sure each of the modules work kind of independently of each other. That way, it's easier to debug, and it's easier to move from one problem to the other. Right. So see what you need to do first before you kind of start doing it, and then break it down and plan it out and go step by step. Okay, so any questions so far? Is this clear? Like, again, none of this is written in stone, but this is a typical kind of loop when it comes to a typical robotics project. Right. Okay, so again, 1, 2, and 3, do it as quickly as possible. Complete it as soon as possible. That's the easy part. The fourth component is going to be what's going to take most of your time. So once you break down the problem, second thing is figure out your timeline, right? Which is going to be super important, right? So take each of these sub problems and allocate which week. Look at how much time you have and kind of allocate each of these tasks to a specific date and have a deadline for each of these tasks. Because if you don't set a timeline for yourself, it's going to be like time is going to kind of slip away from you. Okay, I have a question. Should we set it so using launch files or just raster? So should we use RVs instead of Gazebo? Okay, so I mean, you can create a launch file. So there's nothing like specifically launch file would just make it easier, right? But it's not that we're going to mark you down because you didn't have a launch file or something like that, right? So as long as your final demonstration works well, that's all that matters. Because at the end of the next 5 to 6 weeks, you have to do a small presentation and show everyone. It's like a 4-minute presentation. So you have to kind of demo your project. So what we're really looking at is the final demo, right? We do look at the code as well, but it's not essential that you create a launch file and things like that. But the launch file just makes it easier for you to kind of do your project. Also, could we use RVs instead of Gazebo? Okay, so RVs is not a simulation tool, right? So RVs is just a visualization tool. So RVs is good if you're kind of visualizing sensor information that's coming out of your robot, for example, right? But for it, you can't simulate things in RVs, right? So there's no physics in RVs. There is no, you can't, for example, build, you can't build, say, a wall or, all sorts of different things. Depends on your project, right? So if your project is like 2 turtlebots following each other, then, I mean, you don't necessarily have to use Gazebo. You can do it in RVs. But for example, if it's a grasping situation where you're kind of trying to detect an object and grasp it, you will have to sort of use Gazebo. Again, I think, yeah, because there's a perception element into this, because you have to kind of sense things and detect things, I think you'll have to use Gazebo, right? Because you need to generate information, right? For example, in your simulation, right? Let's say you have a robot with a camera, right? And then there's an object in front of the robot. So this camera has to actually get information from this object and create an image, right? Let's say, of an object like this. So for that to happen, you have to simulate this object. You have to simulate this camera, right? And then this camera has to actually capture this information and create a camera image, right? It'll be a simulated camera image in the sense that the object is simulated, but from Ross's perspective, what it will be giving out is a camera image, right? It doesn't know whether this was a simulated object or not, but it's created a photograph of that object as if that object was actually there. So to do that, you need a simulation of that object in front of the camera, right? And you can't really do that in RVs, right? RViz can show you this part, right? So once you take the image, you can visualize that image in RViz, for example, but it can't simulate a fake object where you can then simulate a camera and detect that object, right? So the reason Gazebo uses so many resources is it's simulating the sensor itself, it's simulating this fake object, and then generating that image, right? But if you want to visualize that image, then you can use RViz. I hope that makes sense, right? So all the simulation bit has to be handled by Gazebo. So how powerful should the GPU be? I mean, you should have a decent enough one. Like obviously you don't need to have a high-end like RTX like 2080 or the new 3000 series or whatever, but like a generally decent GPU would do the job. Yeah, just yeah, obviously you can't get like you'll have to spend a lot of money on something like that, but yeah, I think like a general laptop that, I mean, that can run Windows without any lag should be enough for the Gazebo simulation. There might be a bit of lag, it might be a bit slow, but you'll have to deal with it. So that's why at the start of the course, I also mentioned that dual booting might be a bad idea and things like that, because it just makes it additionally slow on top of everything else. But yeah, unfortunately, this is a issue when we're having to deal with simulations. Right? And it's not an issue we generally face in our course because usually we work on practical hardware, but since last semester, yeah, unfortunately, it's a bit of a problem. So if you're working in a group, maybe let the simulation be run on someone's computer who can actually handle it. So another thing you can do is you can simulate everything in Gazebo and then record a ROS bag, right? You record a ROS bag. So for example, if you're dealing with this perception problem, right? If you're just dealing with getting information from the robot and processing the sense information, you can just record a ROS bag in Gazebo, right? And then you don't have to run Gazebo after that. You can just play the ROS bag and then process that information, and then you can develop your algorithms. Right? You can develop this part of your problem. Yeah, this part of your problem, right? Everyone can see my cursor, right? You guys can see my cursor, right? Okay, cool. Yeah, so for example, in this part, you don't always have to run your Gazebo simulation. You can, because it'll be annoying, I get it. Like, especially when you're debugging code, you'll have to make mistakes, rerun the code over and over again. So in a situation like that, use ROS bags, right? Obviously, when you're doing this part of the problem, though, when you're dealing with the control part, you will kind of need your simulation running because you need to publish information, and you can't kind of do that on recorded data because you kind of need to control things and change things. So in that case, you can't use a ROS bag, but for this half of the problem, you can use a ROS bag, right? Actually, up until this making decision part, you can use a ROS bag, which will make debugging your code very easy. But then when you're actually publishing information back, you need your simulation because you want to kind of inflict change on the simulation. All right, so I hope that answers your question. So back to what we were talking about. So yeah, just make sure you allocate everything in your timeline, each of these different components. One important thing when you're making the timeline is be aware of what you call the planning fallacy, right? Planning fallacy, which is basically humans tend to underestimate how much time it's going to take. So, for example, if this has been seen in a lot of government infrastructure projects, like whenever there's like a new highway that needs to be built or something like that, it usually takes several months or sometimes even years more than what was originally planned, right? And way more money than it was originally planned, right? So humans tend to kind of underestimate how much time it takes. So give yourself plenty of time, right? Make sure you start now don't waste your time, especially because each of these parts, right? This part, this part, this part, this part, each of these parts are going to be frustrating. It's going to be difficult because it's the first time you're doing this, right? You never set up a simulation before, unless you have, but most of you probably haven't, right? So there is a small learning curve to each of these sections, right? So trust me, like even at this point in my experience, like there's all like dealing with open source software, dealing with robots, things will always go wrong, right? So it's like what we generally refer to it as Murphy's law, right? Whatever can go wrong will go wrong always, right? So when you're dealing with these kind of things, just give yourself enough time. Expect to be frustrated, right? Even the most experienced people will still get frustrated when you're dealing with it. Like your code might not work, you don't know why, and then you'll have to spend like a whole night trying to debug your code. Like it's part of the process, right? So don't feel like you're stupider than everyone else or anything like that. Everyone goes through it. Like everyone I know who's doing PhDs and who's like my experience during undergrad, like whenever you're dealing with a project, expect things to go wrong, expect things to be difficult, and understand that there is a learning curve associated with each of these sub problems that I pointed out, right? Even something as simple as setting up the simulation. So most of you, I think, have already started on that, and you've already run into quite a few problems, right? So one of the skills you will be learning is the skill to debug, right? Whenever something goes wrong, like that's a skill in and of itself, how to kind of debug problems and figure out solutions. Right? So obviously you can always ask me, but I'm also really busy. So sometimes I might take a while for me to reply to your emails. So learn how to debug your code online, like how to look through forums, read through documentation, and try to solve problems. And it's this process of debugging, that's where you learn. That's where you kind of learn how to, like even Ross, right? Obviously you can watch a couple of tutorials, but until you actually implement these sections and run into problems and find the solutions to those problems, I don't think you can learn Rust by just looking at a few YouTube videos or reading about it, right? So robotics is a very practical, skill-based thing, right? So the only way you can really gain that experience is jumping right into it and doing it, right? And I think a lot of people face the problem of feeling like you're too dumb, or like especially when you get stuck on a problem and everything looks really complicated, you might not understand the code that other people have written and things like that, and then you think, okay, I'm really stupid, like why am I like this? Like you feel really low, and that doesn't help, right? The important thing you need to realize is everyone goes through this problem, especially when they're learning something new, right? And this course has a lot of things that are new to a lot of you, so it will challenge you. The only thing you can do to help yourself is give yourself enough time, right? And which is why I said, even the first couple of weeks when you started this course, make sure you learn MATLAB, right? Make sure you learn ROS, right? The basics of those things, so that by the time you start the project, you don't have to worry about the basics. You can start worrying about more complicated problems. Now, if you haven't done that, and in week 6, you're suddenly trying to learn MATLAB and suddenly trying to learn ROS in a deeper way, you're in a bit of, I mean, it makes your already difficult task much more difficult, right? But again, right now we are in week 6, you still have time. So, I mean, you can still spend some time learning those things. But every day that goes by, time is getting, like you're losing time, right? So don't waste time. Make sure your timeline doesn't fall into the planning fallacy. Make sure you give yourself enough time. Overestimate the amount of time that you'll be taking for each of the sections. And that's where the third component in project management is important, which is teamwork, right? So most of your groups have like 2 to 3 people in it. So make sure you delegate tasks, right? And it's not just important that you delegate tasks. The people who get delegated those tasks need to pull in their weight, right? Because ultimately you're going to be scored together. Like we'll be looking at your individual contribution, but ultimately your final demonstration is what's going to give us the perception of your entire project, right? So like obviously we will be looking into your individual contributions, because the final report has to be an individual report. But if not, like if people don't pull in their weight, it's going to bring down the whole group, right? So teamwork cuts both ways. You need to obviously, if you're the lead of the group, you need to delegate tasks. Don't try to do everything yourself, because that's impossible. And on the flip side, the people who get delegated tasks, you need to contribute, right? And if you're stuck and if it's taking too long, get help from your teammates, right? And say, okay, this problem is quite difficult, I'm stuck. Don't let it like don't let it fester, right? Like for example, in this timeline, if you are supposed to finish a certain task in 1 week, right, and by the end of that week, like you've faced a lot of problems and it's just not working, address it as soon as possible. Get your teammates involved. Like communication is also important here when you're talking about your teamwork. Talk to your teammates, say, okay, this is a potential problem we're going to have. I've tried my best this whole week, it hasn't worked out. What are options now? Like, what can we do? Maybe you can get someone else to look at the problem, right? Or you can contact me and then we can like solve the problem. Don't wait, because what's going to happen is the weeks will go by really fast, and then ultimately you just have 1 week left, and then you just be stressed out, you'll be depressed, right? And you don't have enough time to finish everything, and then it's just going to be like, I'm telling you all this because I've seen it happen over and over again every semester, right? And it's like usually the groups that do well are not necessarily always the smartest groups. It's the groups that started early and stuck to this timeline, and made sure that they do the amount of work necessary every week, right? And I know it's really difficult right now, and that basically brings me down to my fourth point, which is basically stick to the plan, right? I know that's quite obvious, but I think it's important to talk about it a little bit, because right now, especially with like the quarantine and like all the crazy stuff that's happening in the world, like it's it's a quite a like psychologically depressing time, right? Like you open up any social media app, you're like hit with all this like the world is like falling apart, and like I know how difficult it is, especially to stay focused, stick to a plan, and do all of that, especially because like time itself is like really fluid and weird right now. Like um like the day goes by so fast. You wake up in the morning, next minute like the day is gone. But then when you like look back to last week feels like a month ago. So it's like your sense of time is all screwed up. You're stuck at home, like things. I get how difficult things are for most of you. So use this project as a way to kind of help you get out of it, if anything, because ultimately, like you know ultimately by the end of the next 6 weeks, you will be designing a fully functioning robot, right? And that itself is really cool, right? So try and realize how cool that is, like what an achievement that's going to be by the end of this course, and give yourself that motivation required to kind of stick to the plan, because you can end this semester on a high note and feel good about yourself, that at least that you did your best, right? And right now that feeling of like little accomplishments matter, especially during this like really turbulent time. Like some sort of win right now helps, right? Helps you psychologically, right? So maybe reduce your interaction in social media a little, focus more on your work, and at least that's worked for me a lot. Like putting yourself and focusing on these little problems helps you deal with what's going on outside of all of this, right? So yeah, just make sure you stick to the plan, and try not to lose that sense of urgency and sense of um, kind of focus during this time, because you let 1 week slip by, especially at this moment, since you have about like 5 to 6 weeks, things will become more and more difficult, right? So I'm here to help. Just email me anytime, and I'll set up a meeting after class so that we can discuss whatever issues that you have in the project. But try your best to make progress every week towards your final goal, right? And the advantage of kind of breaking it down into these sub problems is that you don't have to deal with all of this at the same time, right? So for example, when you're thinking about the simulation setup, you can forget about, like processing the information and things like that for a bit and just focus on this problem, right? That way, like otherwise what happens is if you look at the whole problem as a whole, it becomes very daunting. And if you're trying to solve everything at the same time, it becomes quite difficult to debug problems, right? So try your best to break it down into these like sub problems. Like even each of these blocks will have sub problems inside of them, right? So try and take that kind of modular approach to things and trust in the process. Realize that it's going to be frustrating, it's going to be difficult, and be strong and have a sense of perseverance, because that's how you learn. And by the end of it, like every semester, every group does. I mean, if like people your age finishes this project by the end of the semester, right? Like it's been happening for the last like couple of years, right? So you can do it. It's difficult, but you can do it. And yeah, the key important thing is give yourself enough time and stick to the plan and make sure that there is enough teamwork. Okay, so that's really the end of my rant. If you guys have any questions regarding this, you can ask me now before we move forward. Any questions? Okay. Yeah, so good luck with your projects. Hope you guys will do well this time. We had quite a lot of groups do really well last semester, so I'm looking forward to seeing what you guys got. Okay. Yeah, let me stop this recording for a sec. So I'll upload this video as well. And now what I'll be discussing is, well, let's look at transformations a bit, and different coordinate frames and things like that. And after that, I'll do a simple example of how to read information to MATLAB in real time, right? So it's basically covering this part of the problem, basically how to get information from a robot into MATLAB. Okay, so to do that, I'm actually going to use the fetch robot as an example. So if I start the fetch robot simulation, right? So I started the fetch robot simulation in Gazebo, right? And I'm also going to say add an object in front of it so we can look at the camera image of that object. Let me add some color to it. Yeah, I think might be different settings and things like that. So maybe have a look. Change some colors here. Cool. So we have like a red block now. Oops. I don't know why I closed. Just kind of close the model editor. Right, so we have a red cube here. Right, cool. So let's, and then we have the fetch robot, right? And the fetch has some cameras in front of it, right? So the first thing you need to do is let's look at what sort of information we're getting from the fetch, right? So if I type in lost topic list, I get all these different topics that the robot is publishing, right? So just to connect it with what I was talking about here, we have a robot, and the topics are basically all this information the robot is publishing, so that you can subscribe to that information and listen to the sensor information, as well as some of the topics will be control related, right? So for example, you would have, you can see here information about the gripper joint positions, right? So topics like that, you can publish information back, right? So that you can control, say, the gripper arm and things like that, right? So there are some topics in here that will be sensor information that you can extract coming from the cameras, right? And if there's a LiDAR, it will be coming from the LiDAR. And then there are some topics in here that have to do with controlling the robot, right? So one aspect of setting up the simulation, you look at what sort of topics the robot is publishing, and then select the topics that you want to subscribe to, the topics that you want to listen to if you want to get information out of the robot, and then look at the topics you want to listen to, you want to publish back to when you want to control the robot, right? So try and identify them out of this list, right? So let's just look at the camera image, right? So obviously head camera RGB image raw should be camera image, right? So if I type in ROS topic echo and give the name of the topic, you'll see this is the camera information coming from, right? And then I told you about image view, right? I type in image view. Image view. Okay, sorry, you should use RQT image view. There we go. And then if I choose this, you can see I'm seeing the cube, right? So if I look at this and I, for example, move the cube, you can see that this is the camera image, right? And the cube is moving, right? So this is what the robot is seeing right now, right? And this is the reason we're using a simulation, and you can't really do this kind of thing in RViz, right? So if I run RViz, for example, so in RViz, I can visualize what the robot is seeing. So for example, if I put out the image topic, Yeah, there we go. So here in RVs, I can visualize the camera image, right? But for example, these objects and stuff, I can't move them around here in RVs, right? But RVs can help you visualize the data. Okay, so now we know that this topic that I just visualized, what's the topic? Head camera RGB image raw contains the camera image that you're gaining from Gazebo, right? So if this was a real robot, right, everything that I just did now would be the same, right? For example, if I took image view and I looked at this topic, instead of the simulated bird, I'd have real images, right? So that's what I mean by from Ross's perspective, it doesn't matter whether it's real hardware or simulation, right? The topic that it's publishing will give you similar, like it will just give you a camera image, right? So this is it's a camera image of a simulated object, right? That it's in. So for example, this ROS topic list here would be pretty much the same if you had a real robot. Okay, so now you know which topic to look at if you wanted to get the camera image. The topic is basically this, right? Head camera RGB image raw. That should give you the camera image. So let's look at how we can kind of get it onto MATLAB. So if I launch MATLAB, okay, so to actually subscribe to a topic, you need to write a subscriber, right? So so if you just Google MATLAB ROS subscriber, you get an example of how to write it and everything, right? So it's simple. It's just a couple of what do you call it? Couple of lines of code, right? So let's just you need to start with something called ROS init, which is basically creating a ROS master in MATLAB. So let's just quickly put together this code based off this, right? And we'll try to read this camera image in MATLAB in real time, right? So for example, while it's changing in MATLAB, changing in the simulation, that information will be updating here in real time in MATLAB, right? So ROS init connects to ROS master, and then we need to create a subscriber. Let's just test. So you create a subscriber and you need to mention which topic you want to read, right? So what's the topic we want to read? We want head camera RGB image raw. So by the way, you can test this by playing a ROS bag as well, right? So while the ROS bag is playing, you can connect to ROS and try to read the information coming from a ROS bag in real time. Now you have to, I hope it's clear to you that in previous examples in the tutorials, what we did with ROS bags is not that we read the ROS bag in real time, we loaded the ROS bag onto MATLAB offline, right? So we kind of, instead of playing it in real time and accessing the information in real time, we loaded it onto MATLAB, the whole ROS bag in its entirety, and then we access the information inside of it. That's different to running the ROS bag, playing the ROS bag in real time, and then accessing the information. I hope that difference is clear, right? So I've subscribed using this line, and then to actually receive the message, I use receive, which is basically once you have a subscriber, if you receive information, it will be stored into this variable called message, right? And if you want to look at, so if you just run this, so now it's read the image, right? It's read this message, and I have this variable called message 2, So if I looked at this variable message2, you can see that it's received image, and it's a 480 by 640 image, and it has all this information, the header, the width, and the actual data which is in here, right? So if you remember, if you want to actually visualize this image, you have to, so right now this is where all the data, image data is, right? So if you actually open this up, you can see this is all the image data, but it's not in the MATLAB matrix form that we can actually visualize it. So we have to convert it from a ROS image type to a MATLAB image type, right? So you can use this function called read image. So this is the same function we use when we were reading information from a ROS bag, right? And now I'm converting this message2 into a MATLAB image type, and now I can use, say, IMShow. And if I run this, so I need to run ROS shutdown to start it again. Yes, it's already started. See, now I'm kind of getting the same image in MATLAB, right? So I've done this now in a couple of steps, but if you want it to continue over and over and over, what you would do is you would create an infinite loop, right? So you would create a while loop and say give it an infinite condition, like while 1 is greater than 0, right? So now it will continuously do this, right, and update it without exiting, right? So so let me put semicolons here. So now it's continuously updating, right? So for example, now I have the IMShow image here. Now in Gazebo, if I move this, you can see in MATLAB the image is changing, right? Because I'm continuously updating the information, right? So you can see it's very easy to connect ROS and MATLAB, right? So this is basically the same structure you'll be using to subscribe to any information. You write this line, receive the message, and whenever the message is received, it will be stored in this variable, and you can open that variable to kind of understand whatever data is in it. And if you want to, you can visualize it using IMShow. So this is an example of camera information. It's the same if you had a laser, right? So if you had a laser, you'd subscribe to the laser information and then receive that information, and then you can do whatever you want with that information, right? And again, for example, like if you want to speed up everything, you don't even need to visualize it. So visualizing it is for your benefit, right? You can remove that, and you know that the data is in this variable called img, right? If you open it, I'll actually stop this. If you open the variable img, okay, so it says here that there are more than 524,000 images. So you can actually see it, but it will be a grid, right? So you can see here the structure of it. It's a 480 by 640 by 3 matrix, which is the image format that we are used to seeing. So you can just Google like ROS and MATLAB, and you will get you'll get information how to write a subscriber. And let's say, so that's an example of subscribing to information. Let's say you want to control this robot and you want it to move forward. What you would do is you have to figure out which topic you need to publish to move it forward, right? Sometimes you might need another package to help you do that. And then just like you wrote this subscriber, you can write a publisher that will move it forward. So that's a simple example of how you can do that. Now I'd like to finish up by also talking about something very, very important, that is the transformations, right? So I've been talking a lot about transformations, and we've already sorry, RQT TFG, and it will tell you all the transformations associated with it, right? So you'll have a base link to which everything is attached to, right? You have a camera. Hold on. Let me close Matlab before my computer crashes. There's just too many things running right now, right? So all the different coordinate frames that you have to deal with, you can visualize it using this TFG command, right? So you can see, for example, where the camera is associated with the rest of the robot, and you can even visualize it in RViz, right? So if you launch RViz, you can add the transformations, right? So in ROS, you can call them TF for short. So you can add the transformations, and here you can see there's this option called fixed frame. So the fixed frame is basically how you want to visualize, like which reference frame do you want to visualize everything with respect to, right? So if I choose base link, you can see these are all the links associated with the robot, right? I think something small has gone wrong. Let me start this simulation here. I'll just use the teleop command and show you what happens when you move. So it's actually ROSBridge that I was using here, right? So when I was showing you how to connect MATLAB and ROS, what I was using is ROSBridge. So ROSBridge is kind of built into the MATLAB robotics toolbox. Hold on. Yeah. So if I launch the teleop function, I can control the robot using my keyboard. And I'll just show you how the different transformations kind of play with each other. Right? So we have the robot again, and if I install it locally. So if I now launch this, I can control the robot using my keyboard. Right? Yeah, so I'm moving the robot now, right? And now if I look at RViz, and if I select the base link, and I add the transformation tree, right? And if I move the robot now, right? You can see the robot is moving in Gazebo, but it's not moving in RViz, right? Why is that? Because the frame that I'm looking at, the fixed frame that I'm looking from, is the base link of the robot, right? So the base link of the robot is somewhere here, right? So if I'm looking at the movement from the base link, right, it's not going to move, right? Because my fixed frame, my reference frame, is the base link. So the robot is not moving relative to the base link. It's moving relative to the world, right? So I'll have to change my fixed frame to some sort of external frame to, yeah, so right now there is no external frame here, but you need, what's that? Let me start a different simulation. Yeah, I think yeah, you need to launch the fetch navigation package as well, I think, to visualize its odometry messages, but you get the idea, right? So in RViz, you can visualize those different transformation trees. And this fixed frame over here is basically which reference frame are you looking at to identify the movement and things like that. And you can change that to any of the available frames in the robot. So if you pick a frame that's in the robot itself, obviously the robot's not going to move, but if you pick a frame that's outside, like the odometry frame or a map frame or something like that, you can see the robot kind of move in the world, right? Okay, so I'm going to wrap up there because it's 3 o'clock, but we'll continue this discussion as we go along. But yeah, understanding the different transformation trees and the different coordinate axes that are there is important, and you can actually visualize all the the transformations here. For some reason, my transformations are seem a bit screwed up for some reason, and I don't see the camera transformations here, but I think that's some sort of small problem in my setup of the fetch robot. Yeah, because I should get the camera frames and everything up here as well. I'll figure that out, and we'll continue this discussion next week. But just remember, the TF is a very important thing because it will tell you, show you all the different coordinate frames in action. And for example, if you're getting images from a camera, it will be coming to the camera coordinate frame, and then you'll have to kind of transform it from the camera coordinate frame to the base one, right? So everything about ROS transformations can be found if you just Google ROS TF, right? And here in the wiki page, it will give you the tutorials. And I think if you do the introductory tutorials as well, then will be a section for introducing you to this concept of transformations, right? And the thing is, you can listen to those transformations and you can get those transformations. For example, if you want to figure out where the arm is relative to the base of the robot, you can kind of subscribe to that transformation tree that I showed you and get that information. Right? So all that stuff is here in the tutorials. And if you need more help, we can keep discussing them further. So here is an example of transformations. It tells you what they do and why we use them. There's a whole bunch of tutorials, so you can listen to those transformations and you can broadcast transformations yourself, like subscribers and publishers. So I just wanted to mention that because it might be useful in your projects. Okay, so let's wrap up there. I hope this session was useful. I'll upload these videos by the end of today. Yeah, in the meantime, please go check the playlist out and watch the necessary videos under controls. And I think StuVac is coming up. Use that time wisely. You won't get free time like that for a while. So plan out those couple of weeks and do your best to make a lot of progress with your project and give yourself enough time to keep moving forward. Yeah. So thanks a lot, guys. So I'll stick around for a couple of minutes. A few of you have some questions, so let's try and address them. Okay, so I had a couple of emails also from a few of you, so let's try to address them. Okay, so who wants to go first? It's quite a few of you had a couple of problems. Joseph? Yeah. in C++, we can run callbacks and methods on different threads. Can we do this in MATLAB? I think there's a parallel processing toolbox in MATLAB. I haven't used it myself. I think you can give it a try. But yeah, like C++ is the way to go if you want to do some parallel programming. And you want different threads and all that stuff. So I don't know how much parallel programming support MATLAB provides. Yeah, just try and maybe Google and see. I think it does provide parallel processing opportunities. Again, I don't know how well it kind of meshes with ROS as well. So yeah, if you have experience working with C++, then if you think it'll be easier for you to work with C++, yeah, you can use C++. You can use C++, Python, or MATLAB. It's completely up to you. There's no limitation that you have to work with MATLAB. So if you're comfortable with using C++, go right ahead. No one is stopping you. Yeah. Joseph, you should be able to share your screen now. Can you show me the contents of your cat-king package? Just open it on. So what is LiDAR? Which LiDAR? Which laser? So the fetch robot's LiDAR should be automatically being like published. You don't need to separately read it. Also, does the fetch have a LiDAR to begin with? I don't think the fetch has a laser, it just has a camera, right? Yeah, the fetch only has let me check. Yeah, it just has a camera. It just has a RGB camera. It doesn't have a laser or light or anything. Also, if yeah, like the simulation should be publishing that information. Depends, like where did you find this scan package? Okay, so just say ROS topic echo base scan. You missed the C. Slash press tab. Yeah, so you're getting the scan information. You don't need a separate package to read the scan information. So all you have to do is subscribe to that topic, and then you can, just like I showed you today in MATLAB using the camera image, you can load that into MATLAB. Or if you want to code in C++ or Python, all you have to do is subscribe to that topic, right? The slash base scan topic, and then all this information in your laser scan will be available to you. Where did you find this scan package? Because like different people might have written it for different. All right, it's inside the show me a Catkin workspace. Okay, go into source. No. So go out to source. The LiDAR reader is a separate package that you have downloaded from somewhere else. So I don't know where you got that from. Oh, right. So you're trying to. Okay, so you're going to. Right. Okay. That makes sense. So you subscribe to the base scan and you're trying to read it. Right. Okay. That makes sense. Okay, so you're just trying. Yeah. Okay, you're trying to create basically a separate package to listen to the information so you can process it. Okay, so yeah, and you can't make it because have you the package.xml? Do you have experience with C++? Okay, then if you don't, I think it's best to stick to MATLAB, right? So for example, if you want to read the laser information, you just have to write 4 lines of code and do what I did today, basically. So instead of reading the image, you read the laser scan, and then you have all that information in MATLAB, and you can process it any way you want. Now, it's completely up to you if you want to work in C++, but then like it's going to be very, very hard unless you have experience in C++, because like there's a lot of different things you have to worry about. But I think you should, if you don't have experience, I think with the short period of time you have, I strongly suggest using MATLAB. Right? Because, for example, I think the error that you're dealing with right now is there's a XML document called package.xml in every ROS node that you write that has to be properly set before you can build it. Yeah, and the CMake list also has to be properly set. Right? So yeah, debugging this is going to take some time, man. Like you have to sit down and see where the mistake is.
Hello?
Yeah.
Oh, can you hear me?
I can hear you. Yeah.
So the error I was getting is from this line here.
Mm-hmm.
But if I comment it out and then build it, it runs fine.
Right. So you have added a dependency that's the same name as the package that you're trying to create, which doesn't really make sense, right?
So right. So how would you? Isn't that what you're meant to do?
No. So dependencies are like other libraries and things that that your package depends on.
Okay.
Right. So you've the name of your package is already LiDAR reader node, right?
Yeah.
So it can't depend on itself, right?
Okay.
It's not an external external package. Are you adamant about going like using C++ or because it's like 4 lines of code in MATLAB to get all that information out?
Yeah, well, because I kind of already started in C++. That's all. Because I don't know, it's just what I picked. I didn't really think about using MATLAB because I think our group wants to use C++.
Okay, so the thing about ROS is you can design different components in different sections. So for example, you can do your section in MATLAB, someone else can do their section in C++, and they'll all talk to each other, no problem. But I think that's a conversation you need to have with the rest of your group and decide how to move forward, because like it's going to be difficult. I won't lie, like C++ can be really frustrating. Because you have so much control over every aspect of it that it's okay. So like for example, like you're writing an entire package now to do the 4 lines of code that I just showed you on MATLAB today, right? Which is just subscribe to a topic and.
But with the MATLAB, if you're using it in MATLAB, how do you how do you get it onto the simulation to run automatically?
So you launch the MATLAB, you run the MATLAB script, and then you launch the simulation. And if the topics from the simulation are being published, MATLAB will read them. I mean, it's the same as, for example, if you wrote this package now, and you launch this package separately. It's the same. It's like just a different module. It'll just be, so your simulation will be publishing laser scans continuously. And then at the moment you start your MATLAB script, your MATLAB script can subscribe to that topic and listen to the information. And then you can do all the processing in MATLAB, and just like you subscribe to a topic, you can publish back some sort of message back to your simulation, and it will execute it.
So do you have to have MATLAB open when you're running the thing?
Yeah.
Okay, because with this you don't have to have it open, right? Because with this, if you just
yeah, so this is not MATLAB. You'll be running a separate executable package. So it will also be running some sort of package. So it's like you have to run your program, right? So in MATLAB, you would run the program on MATLAB. Here, you would run it on your terminal, and it will be running in the background.
Yeah, fair enough. Yeah. Okay, I got it. All right.
Well, yeah, it's just using a different language, right? It's doing the same thing. It's listening to the information. And then there's just like the ROS bridge functionality translates everything into MATLAB. So you can do everything in MATLAB. And then you can publish it back into ROS. And then, I think that would be fairly easier, especially since you don't have much time to learn C++ from scratch.
Fair enough. I'll see. I'll think about it now that you've mentioned it. Yeah. I think that's it. Thanks.
Like even I think Python would even be easier than C++. Yeah. Like if you had some knowledge in C++, like then
I have a little bit. Like I did what's it called? Programming for mechatronic systems, but like I dropped it. So I did like a couple of weeks of that subject.
Okay, so yeah, I mean, it's up to you. Like,
yeah.
It's just like I'm just telling you the easiest way forward.
Yeah, I get it.
Because the project itself is going to be tough to begin with, and if you are stuck at small stages trying to like read information and stuff like that, it's just going to make things difficult. But if you want to challenge yourself and do that, and if you're confident in yourself, go right ahead. But if I was you, I try to be making things easier for myself, because this is not programming for mechatronics, right? We are not forcing you to do it in C++. Like what we care about is the robotics application, and it doesn't have to be like a super optimized code that can run in the real world, like flawlessly. Like that's not what we're testing. We're not testing your coding skills. We're testing your ability to kind of connect the dots and do the whole, like the big picture, like the perception part and then the control part, and like put them all together and create one kind of cohesive system. So we don't really worry too much about which language you're using to do that. So because we don't care, like you could just get away with using an easy way to deal with it, because that will reduce the complexity for you, the frustration.
Yeah. All right. Thanks.
No worries. Also, like most of the tutorials, like if you watch the videos on YouTube, they're all done in MATLAB, so it will be easier for you to transfer the knowledge.
Yeah,
Like
true.
we did an entire tutorial on laser scans, right? Like how to visualize the laser scan information, how to use ICP, all that stuff, right, in MATLAB. So it's like part of your project is already done. All you have to do is get the information onto MATLAB, and then you can process it in MATLAB using the stuff we covered in the tutorials. So it's like, why make the job harder than it has to be, you know?
Fair enough.
Okay, cool. Let's move on to the next.
Yeah, hi. Okay.
Hi, Sharice.
Hello. So I'll share my screen. I've just like got my audio on one computer and my screen that with the Linux on another screen. So
Yeah, no
one
problem.
sec. This one. Okay. So what I did is I followed all of the steps in the PDF document for the Gazebo simulation setup guide.
Mhm.
And then initially I was able to open the like Turtlebot in like the empty world.
Okay.
And then I was trying to open up the teleop things.
Mhm.
And then I was getting this error to say that like the resource isn't found, and now nothing opens.
Okay.
So I like what I did is I like redid my catkin make, and I like checked I did my source devel bash
Yeah.
and like made sure that that's like all good. But I've kind of run out of ideas.
Okay, so let's figure it out. So there's a package that's missing called turtlebot3_bring up.
Yeah, so when I look in the file manager, that folder is there and it has things in it. Which one was it in? It was in
So when you built it,
this one.
yeah.
Yeah, it's all the launch files are like in there, so it exists.
Okay, and when you built the packages, everything got built with no problem.
Yes, yes.
Okay, so let's try building it again. Go to your Catkin workspace, and I think the top left corner.
Is there a shortcut to get back to like there quickly? Or
No.
okay.
You can just CD and give the path.
Okay. Yeah.
Okay, source the thing.
Yeah. Yeah.
Okay, launch it.
So yeah, I can just launch it back through this one where I had it before, right? So I still get the same errors.
Do you have like multiple Catkin workspace by any chance, or is it just this?
Hang on. So if I go home, there's just this one, Catkin workspace, and then there's just this three. So that's it.
Okay, so type in ROS launch.
Yeah.
Oh, right. Okay. So you're not mentioning the package name.
Oh, that gave me a different error when I did that as well.
You need to mention the package name. So ROS launch.
So yeah, okay, ROS launch.
Space.
Yeah.
Just type turtle.
Yeah.
And tab twice, and you get all the packages that are installed.
Okay.
So I think it's turtlebot3_simulation, right? That's the package. Tab twice.
Yeah, then nothing's happening. So when I tried to look before, I tried to do like the ROS package find,
Yeah.
and then that came back with like it can't find any packages.
Okay, is there anything else in that Catkin workspace of yours that's important?
No, it's just set up for sensors at the moment.
Okay, so would you be comfortable in just like deleting it completely?
Okay, sure.
This is like last resort usually.
Yeah. Okay. Rip. All right. So if I just delete this whole thing then.
Mm-hmm.
Okay.
Okay, and maybe create your Catkin workspace in your home directory.
Okay.
And
so I can just delete this for now as well then, so I don't get confused where it is. Delete. Okay. So to create, I can do it here. I can just make a new folder, right?
Yeah.
And then I need to go and clone all the things back into.
Yeah. So let's go through the whole process one step by step.
Yep. Cool. Thank you. So do I need to go?
Yeah, that doesn't exist anymore, right?
Yeah. Okay. Oh, hang on. That's
just a regular CD will bring it to your home. Because now it's inside the trash folder.
Yeah. So then, how do I get?
Just type in CD, just regular CD without it.
Okay. And then I can go CD catkin. Okay, and then I go catkin make.
You need to create a source folder first.
So, okay. So I go mk. C.
Okay, so yeah, do that, and then could you also make a separate folder in your home directory called Git? Because see, like if you have trouble in your Catkin workspace in your build environment, what you can do is you can actually clone all your packages to a separate folder, and then you can just create shortcuts in your Catkin workspace so that if you have to delete your Catkin workspace, everything that you've downloaded still exists, and all the changes that you made also in the code will exist, right?
Okay.
So I'll just show you how to do that.
Yep.
So that's usually the standard practice, like if you want to do it. Or you can, I mean, there's nothing wrong with directly cloning it into your Catkin workspace, but usually you kind of separate the two so that if things go wrong, they're kind of set in different folders. Right?
Yeah.
So can you navigate into the Git folder?
Yeah.
And now clone everything into that folder.
Can I just do that in the file manager so I can? So I can just copy paste it, or
I'll show you how to do it first.
Okay.
First clone it to the Git folder.
So just
no, as in like Git clone the 3 packages in the PDF that I sent.
Oh, okay, sorry. Okay. Okay. Oh.
Okay. Cool. So now what we're going to do is we're going to create shortcuts in the Catkin workspace to these 3 packages. So to do that, type in
ln
minus ln space minus s.
Yep.
Right. So minus s stands for symlink. So you're creating something called a symbolic link. Right. Space.
Yep.
And now basically give the path to the the first thing you clone, 12.3 underscore messages. So basically slash
Yeah.
Home.
Is it actually called home or is it?
Yeah. / Cherise. You can tab and then it will just do that. And then git.
And
And tab. And then 12/3 underscore messages, right?
Underscore, yeah. And then does it need to also be .git?
No.
Okay.
Just the folder, right? And then space.
Yeah.
And now give the path to where you want it to link to, which is home, Cherise, Catkin workspace.
Yeah.
So this is kind of like the safe way to clone things.
Okay, and then that's then into the SRC. Yeah.
Good. And now enter.
Yeah.
Now go to your file browser. I'll just show you the difference. So now go to your Catkin workspace.
Wait.
Go to source. So you can see that it's like a shortcut to the actual file. So now you can kind of delete the Catkin workspace, do whatever you want to it, but the original files will still always be there in your Git folder.
Oh, okay. Yeah.
Right.
Yeah,
so now
awesome.
do the same for the other 2 packages as well.
Yeah. Okay. So,
You can just press the up arrow.
and then just delete.
Yeah, just delete that bit.
So Tettlebot messages is just Tettlebot.
By the way, did you guys change your proposal and send it?
So we're doing project 7 instead.
Okay.
He let us keep, because we just misinterpreted the project altogether.
Yeah. So I didn't mark your proposal yet. I'll do that.
Oh, okay, yeah. So that's yeah. Okay, cool.
Okay, cool. So now go to your Catkin workspace and build it.
Yeah. Okay. Awesome. Okay. No errors there. And so then I need to do the source devel setup.bash. Yes. Okay.
I'll try running it.
Try the launching it again. So do I need to go into the folders to launch things?
No, you don't have to. So the reason you're doing that source devel setup bash thing is you're kind of giving the path to your bash, which is basically this tiny piece of text that connects your terminal with all the libraries that you have.
Oh, okay. So that one worked.
Yeah.
Nice. Okay. Can I just make sure that more than just that one works? Because last time I got one working and nothing else worked. So do I just need to open up another terminal to run something else?
Maybe not. Don't run both at the same time.
Oh, okay.
Because it's
maybe that's why it was crying on me. So if I get out of it, so you just Control C to like close it, yeah?
Yeah. Also, you need to specify which version of the Delbot you're using, right?
Yeah. So in the I guess I need to do that again in the bash RC, the waffle model. Yeah. I'll just make sure that this one works as well.
Okay, right. So your teleop has to run along with the simulation. So the teleop package is basically it gives you the power to control the simulation using
yeah.
Okay, so that's what you mean. I thought you were about to open a separate simulation.
Oh, okay, no, that's because yeah, cool. All right, that kind of solves it. Rachel, is yours working now? So Rachel was just kind of following along as well.
Okay.
Yeah, she had the same problem as me.
Okay, so can you actually run both and see if both of them work together? The simulation and the
so they need to both be run in separate terminals, correct?
Yeah.
Okay, so
they're like 2 different ROS packages, 2 different nodes in your so it's like independent modules that you can kind of launch to do different things, and they all talk to each other using ROS topics.
Yeah.
I think that path doesn't exist anymore.
Yeah. So
Just
what was the shortcut to get back to
just
this?
CD, just regular CD. It takes you to home.
Yeah.
Yeah.
Cool. Okay. So and then from there I can.
Yeah, you don't need to be in Catkin Workspace to launch.
Oh really? Okay.
Same.
Okay, so this is the thing, right? So you sourced the Catkin Workspace in the other terminal, but you haven't. Maybe it hasn't sourced here. So. Yeah, try now.
Okay.
Yeah, so move your keyboard and as in like use your keyboard to move the, you need to be in that particular terminal.
Okay. Oh yeah, cool.
Okay,
Nice.
awesome. Also, just to make sure that you know, all this, like you don't have to source every single time. I'm going to send this command in the chat.
Yep. So what does that line
So
mean?
that permanently adds that command onto your bash RC.
Okay, so I should write that in.
Yeah, just type it out in any of the terminals.
So do I need to be inside the Catkin?
No, you don't. You
Work.
just copy paste that command.
Oh yeah. Okay, what's this? Where's the Zoom? Zoom. Oh my god. Where did it go? Where's the Zoom chat gone? Yeah. Okay.
Cool. And go to your file manager, and you can see your bash RC file there, right? Right at the bottom. Yeah.
Yes.
So scroll down, and you can see that right at the bottom you added that line.
Oh, okay, perfect.
Yeah. But I think every time you build it, though, I think it's best just to be safe and source it. But now, like it should work in every single terminal without problem.
Yeah.
Every terminal that you launch will already automatically run that command.
Okay. All right, cool. Yeah, thank you very much.
No worries. Okay, so who's up next? Nicholas and Grant? Who wants to go next? Or is this it?
I have a question still, Marlene. Because I was just following along with Charisse. I'll see if I can share my screen. But
Sure.
when I've run the teleop thing, but just every time I press like a key, it seems to be working, but the robot doesn't move.
Okay.
So, okay. Yeah. Is there a way to just share the whole screen, or can I only share like?
You can share the whole screen.
Okay. I'm not sure how to do that.
So there's a
share
button. Yeah, there you go.
Is that it? Okay. It's just a portion of the screen. That's. I don't know what's happening there. Okay. I don't know. Like, okay, if I go down here, it says that it's working.
Yeah.
Every time I press a key. But if I actually like do it, the robot doesn't move.
Okay. Can you go to your simulation?
Sorry, to the.
Yeah, to the Gazebo simulation.
Oh, the Gazebo. Okay.
Yeah. Just press outside of the robot, like in space. Yeah, it's great. I think your simulation is kind of like frozen.
Okay.
Go to the terminal with the simulation running and just press Control C. Yeah, I can see a small error there as well.
That one? Yeah, I wasn't sure what that.
Yeah, so if something like that happens, you can just like close it and start it.
Okay. Okay.
Okay.
So I'll just do it again.
Mhm.
Okay. So do I need to?
Maybe restart the Teleop package as well.
Yeah. Okay. Okay, and I'll do that one to see if that's working. Oh, okay, now it's working. Sorry, thank you.
So that's like if you're like really stuck, just close everything, start it again. And
Yeah.
sometimes that
Okay.
works as well.
Thank you.
Yeah. Is that it? Is that it, guys? It's quite a few of you still online, but I'm guessing just like left your computer. So I'm just going to end the meeting now. But yeah, does anyone else have any questions?
Hey, Malene, can I quickly jump in as well if you have some time?
Mhm.
Thank you. I'll just share my screen as well real quick. That's okay. So I'm having an issue where I'm getting this error message. I'm not sure why, just when I'm trying to run my...
Okay, so it says resource not found exactly. So let me just Google that error. Can you type in, hold on. Yeah, just type in sudo apt get install ROS dash melodic dash cycle XA. So, yeah, there we go.
Enter.
Mhm.
What does that mean? Oh.
Use the up arrow again and it will get the same command. Yeah. I think, yeah, it should be apt get, there should be a dash in between.
All right.
Okay, try it now. Can you type in sudo apt-get install? ROS melodic dash fetch dash ROS. I think my setup guide is, so I built the setup guide last semester and everything was working fine, but then I think some of these packages have been like updated and stuff, so things aren't.
Oh, good. Can I?
Semester. Yeah, press enter. You misspelled sudo.
Sorry.
So Daniel, you emailed me, right?
Yeah, I did.
Okay. So now try launch it. Okay, so Zacro apply is depreciated. Please use that instead. Okay, open up the file manager. And so this is the issue with like open source stuff. Things are changing all the time. Yeah, go into Catkin workspace. Source. Fetch Gazebo. Fetch Gazebo. Launch. Include. And there should be fetch.launch.xml. Can you open it on a text editor? It will probably open on your. Okay, cool. So it says zacro.py in the lines. Line above it.
Sorry. What am I looking for again?
Zacro.py.
Zacro.
Up. Yeah, that line. Keep going to the right.
Here?
Yeah. Remove the .py.
Just completely, or?
Yeah, just yeah. Save. Try now. Yeah, now you're missing another package called RGBD launch. So type in sudo apt-get install. So whenever it says resource not found, that means you're missing a package, right?
Yeah.
Ross melodic. You misspelled Ross.
Oh.
Dash RGBD dash launch. Yep. Okay, do the try. It works, right?
There we go. That's much better. Thank you. Oh.
Yeah, close it and try again. Just press Control C.
Control C. Oh, I think my computer crashed.
Yeah, just give it a second.